Okay, so hey everybody, welcome to Fortran.
Sup?
Well, um, today I'm going to be presenting about the Fortran language, and this is to celebrate the brand new Fortran module. You wouldn't know that it was there if you had an existing init.el file, but if you were a brand new user to Doom Emacs and you opened up your fresh init, you'd find your favorite language down there in the list. Is it Python? No. Is it Go? No. It's Fortran, and it's even got great puns. So by the end of this talk, you will understand this quote: "In Fortran, God is real unless declared integer." And it's funny because so I wrote the Fortran module because I was having a lot of trouble getting Fortran like working on a Linux machine for my dad. He specifically wants Intel Fortran, and while I haven't gotten that part of it working yet, the module itself does work, and it's actually useful. The process of doing that and doing this slide deck sort of taught me it, and I learned it's actually got some charm, and it's actually got most of what you would need, um, uh, like for actual like real world modern, fairly modern software development. Um, Subroutine. I grew up hearing the word subroutine, and I always wondered what it was. And even as a professional programmer, I still would wonder every once in a while, like, what the heck's a subroutine? I wish I had one. Um, and today, you too will have your very own subroutines because they are special. Yeah, let's click on. So yeah, today we're going to look at the history of Fortran a little bit. We're going to look at the language itself, and then we're going to look at how like software development actually happens in modern Fortran today. I was pleasantly surprised at what there is, and personally, I would rather write code in Fortran than I would Go. That was the hot take that I made the other day. Um, it's kind of pleasant. By the, can you still see that?
Yep.
Great. By the end of this talk, you will understand uh, all of what you see here. So this represents two files in a project. The first file would be the although this could actually be in the same file. The first is sort of your main that represents the actual program. There's kind of like an implicit function in here. You know, here we are declaring some modules and some imports that we're doing. This is here is a kind of a weird thing. It's like, huh, what's this for? And you have this call keyword on a function, or what looks like a function. I'm using those words loosely. And then here's a module declaration. It's got everything you would want. Look, private declarations of members, explicit exports. Ooh, there's that funny word, a subroutine. Don't you want one? And some simple IO. If you have any questions at any time about like code that appears in the slides, although there's not that much, just shut out or throw something, and because I'm not watching the Discord, and I'll answer whatever question you have. Sounds good.
Yep.
Okay, good. Thank you, active audience. Okay, so the history of Fortran. Um, Quick question: does anyone just not know what Fortran is at all?
I know it's a
I
programming
mean, I
language.
know that it's like a really old programming language, but that's kind of it.
Right. Fortran was kind of the Fortran was kind of it's one of the OG languages. When you think like, oh yeah, C's pretty old. No, C is young. Uh, Fortran is Fortran and Lisp are basically the oldest programming languages, and they've both survived into the modern day. Lisp has changed a lot, like whereas no one really writes Lisp like Lisp anymore. Um, Fortran, that's like half true for Fortran, in that like modern Fortran definitely it has evolved from what Fortran used to be in the original versions, but there's many different sort of like milestone versions throughout its history. A big one was Fortran 66, even though it came out in the 50s, and then Fortran 77. Later there was Fortran 90, 95, and then a few different revisions in the 2000s. But apparently, a lot of Fortran 66 is still written because of there's a lot of legacy code and stuff. And a friend of mine, when I was doing university, was telling me that for his physics degree, and this was in like the 2000s, that that he had to write some Fortran 66 for his courses for whatever reason, even though like the normal compiler GNU Fortran today like does whatever you want. So I have no idea why his professors were telling him to use Fortran 66, and you will see some Fortran 66 today. Um, and there's some interesting consequences of the way Fortran has evolved that does not apply to Lisp. I would say, like today we have different Lisp versions that are like distinct and they have their own compilers, and it's kind of like a family that all have a sort of a cultural connection to the original Lisp, whereas Fortran is still Fortran. Like it's still the actual same language. It just has like evolved, and you'll see what that means. So I had an interview the other day with my dad, and I got him to like tell me everything because he's kind of like we sort of talked about it over the years, and we like to make fun of each other about like he'd always say like I'd say like, oh dad, like we're using all these cool languages, and he'd be like, oh yeah, well real men use Fortran, and we used to do like this and that back in the day. Um, so then from the conversations that we've had over the years, I had an interview with him the other day, and I sat down and recorded him, and I pulled out like all the best quotes, and so I'll be reading some here. So my dad graduated in '73. That was his undergrad, and he did a Fortran. He did a standalone engineering course, like a Fortran course. It was called Fortran Programming. And back in the day, there were no comp sci degree, there were no comp sci programs at universities. If you were going to do programming, it had to be part of engineering. And yeah, apparently the class was full, so it was like people were like really keen to be learning that stuff. And he said that yeah, there was a big card reader and like these huge rooms with all these key punch machines. So you kind of like you and your friends had to go hog one, and you had all this big paper that you had your programs written on, and you'd have to go and you'd have to punch it out. Um, and then feed it into the machines, and you'd make mistakes and there'd be bugs, and so you'd have to like all the cards were labeled because you couldn't fit your program on one card, so if you had a mistake it would kind of like screw with the rest of them. So you'd often say that what you'd do is you wouldn't fill up a card all the way. You would like only write a card say like 3/4 because you'd know that there'd probably be some mistake you'd have to make on that one card, and if you wanted to fix a bug you'd only want to replace the one card, right? If your bug fix like made the card longer than it should have been, well then it's going to overflow into the next cards, and all your next cards are also ruined. And since that was in '73, yeah, Fortran 77 hadn't come out yet, so that would have been Fortran 66. Here's what Fortran 66 looks like. What do you see? What do you notice about this?
There's numbers on the left of all of the code.
What do you think those numbers are?
Something to do with
Memory
punch
addresses.
cards. Which card it should end up on, or where it should like jump to a different card.
Close. Those are go-tos, or like those are like um
Markers, so you can go to that card.
Labels.
yes.
Labels,
Yeah,
yeah.
so the do 10 and do 20.
What we can see here is there's a nested loop here. There's two do loops. This isn't the syntax that's used today, although this still compiles. And it has to do with like and the explicit continue statements aren't necessary either. But you would see that can you see my mouse?
Yes.
Okay, I can do this as well. It's perhaps better.
Yeah,
So
the screen.
we have nested loops here, right? So it goes in here, it's iterating j, we're going in here, it's iterating I, then we actually do the thing, and it's saying continue to 20. So that means it's manually jumping it back here with like a manual go-to, kind of, even though this is like a go-to sort of shorthand. And then it's iterating as much as it wants, and then once I has been exhausted, then it moves ahead, and that says continue up to 10, and then we go up to 10, and then it does it all again. We have an empty return here, which isn't necessary anymore, and then an end. I don't think I put this in the later section actually, but you'll see that 1, 2, 3, 4, 5, 6, that there are 6 white spaces before code starts. This was necessary for Fortran, for like early versions of Fortran. You could not write code on the very left. All code had to be indented 6 spaces. I believe that, and that's a concern of punch cards that that transitioned into, like, once personal computers were actually a thing. It kind of transitioned to how you had to write it on computers too, because that's just what the compiler expected. The compiler expected that space there, and didn't stop mattering for a while. There's also some other weird stuff I'll explain later. Like, you see this weird statement, and there's this dimension statement, and you'll notice that there's like no types. And oh, here's another cool thing: array indexing is done with parentheses, not brackets. That's kind of like a little bit jarring to the eyes at first. So my dad used to work for a company called BC Hydro, and he says that his days there were all in Fortran 66. He spent quite a lot of time. This was like the time where they were really starting to use programming for a lot of serious, like, work. They'd get data from the field, stuff like actual live observations from out there. Say they're trying to, like, I don't know, they're trying to like build a dam, or they're trying to build like bridges way out in the interior or whatever, like building highways and stuff. And they're like, is this soil moving? We think it might be. And they'd send all this geophysical data back to like the labs, the engineering labs at BC Hydro. Instead of doing all the pen and paper stuff, they were writing Fortran to do it. So he said at one point he had quite a lot of autonomy, and he was like writing Fortran like pretty much all day. But yeah, his career, I would say, and later he became a university professor, but he kind of did like a career of writing Fortran. And while I didn't follow in his footsteps in terms of becoming an engineer, I did learn to program. I always made fun of him for his Fortran use, but now I kind of appreciate it. And he told me that Fortran was extremely common amongst his colleagues and like everybody in engineering, and that there was absolutely nothing. There was no need to look at anything else. Like, it was the language. Everybody knew it. Everyone was writing textbooks and papers in it. That was it. Just was. It was like the dominant language for research for decades, and it still is in a way, depending on your field, and also because there's legacy code. Yeah, what's up?
Was there some sort of rivalry between Fortran and Lisp? Sort of like the rivalry between Rust newcomers and I don't know, C++?
I don't know. I think Lisp probably had its adherents, but it sounds like for like the guys on the ground who were used to mathematics, Fortran stands for Formula Translator. And it was what they were doing. Like, Fortran was like one of the first languages that let them write math in code. Like, if we go back here, like this, for instance, feels like math to mathematicians with some extra sort of jazz around it. And so that's what they needed. And apparently Fortran was one of the first languages that let them do that.
Maybe you like talk about this later. But in a sense, why was a lot of people, like, when you hear about the history of programming languages, they say things like, C was like, the first real something.
Right.
What can you maybe talk about, like, what Fortran lacks that made C and other languages like it like overtake it eventually? Or
Fortran still is actually about as fast or faster than C. Or at least it was for a long time, depending on the benchmark that you're doing. Like, I don't even know if anyone's testing Fortran anymore, but like, it's at least in because it's fairly simple. It's a fairly small language. It's probably smaller than Go, actually. There's not a lot to it, like C, right? And so you can get like extremely fast executables, and by this point the compilers have been optimized to the moon. So it was fast. It's always been fast. It's simple, and it was like math. I would say that those were and after a while, like, it's not just the languages, right? It's also the ecosystem. It's the fact that everybody, pardon me, and it let you do matrix operations quite easily. I think that's a big one, is that for a lot of linear algebra problems and things like that, or like big, huge data sets, matrices and matrix operations were quite, especially in Fortran 77, were quite like easy to do. Like you didn't have to fiddle with like dumb like nested loops anymore. Back in the day you did, but in the more modern Fortrans, you just have like matrices are this first class thing, and that's really good for like just crunching numbers.
Arteco has a comment.
Yeah.
This mic's not working. He asked if you can talk about pointer aliasing.
If I can talk about pointer aliasing, Dad never used pointers, and so I cannot comment on that. There's actually a comment later. There's a quote later about how he never used pointers. Read Fortran being faster than C.
I know that it's heavily used in like very mathy programs. I worked on a meteorology laboratory when I joined university, and they had these this very like complex atmosphere climate simulation, and they basically we ran this huge Fortran program that spewed out lots and lots of ASCII, and the meteorologist would then analyze it. And my job was basically to install it on the machines, and it was basically configure, make, install, and they would run it and like melt the Arctic and the Antarctic and so on.
Yeah, that's kind of sort of sounds like what it was. Is they were using it for these really hard like geophysical problems, climate problems, weather problems, construction problems, and it probably still is. There's probably a lot of like Fortran code, like Fortran 66 code, still running in the wild, I imagine. I'm gonna move on then. Tedious programming. So yeah, like way back in the day, programming tasks that we take for granted were a lot harder. Two I'll mention are array processors. So he says there were big breakthroughs in the 60s with array processors. Before these like really nice matrix primitives were embedded in the language, you'd have to call up an array processor, which was a separate machine, and it was a nightmare trying to debug all of the like the data that you would send into it and the data that you would get back, and like the calling statements had to be absolutely perfect, and even then there'd still be mistakes somehow. And when he told me that, it made me think about GPUs, because GPUs are kind of the same. It's this like separate machine meant for linear algebra that you have to call in a special way, and then you can't really debug it very well. So we had a little chat about that. But eventually, the matrix primitives, like better matrix primitives, were added to Fortran. I think 77, and it really made their code more like condensed and clean. And of course, RAM obviously was another one. So he'd say that, okay, if they were working with arrays of dimension 100,000 or so, you'd have to be really careful that you weren't swapping to disk, because then your life would basically be over. Occasionally they'd write arrays to a secondary device, like some like external piece of hardware, and then read it back later on when they knew they had the memory space. And like in the very early days, it would have been writing to tape. Like you couldn't have like more than one of these arrays in memory at the same time. So you have to like write it out, do some of the calculation, dump the memory for that, and read your original array back in. But of course, as time went on, that was less and less of a concern. And then if you were reading or writing this stuff out, you could just write it like maybe to disk and then read it back again, and not to tape. But nowadays we just have infinite RAM and we don't care. So here's the cool thing about Fortran, is that newer Fortran constructions and things can be embedded in legacy code. The compiler just understands how to like compile mixed paradigm code. And he was saying, here's the important quote, that during his career, programming was only one part of their job. Like these guys were like scientists trying to solve problems, right? They had like a lot of things to do. It wasn't just coding. Like for me, I just sort of sit around and code all day. But like, they were doing things other than the coding. And it says if someone came to him and told him that he could program in Fox Basic Zipsy Doodle, and then his program would go 10 times faster, then yeah, of course he'd switch. But really there was like no other language that somebody could like come and say like, oh, just, you know, hey, just let's just switch to this other language and everything will be better. I mean, we kind of do that all the time, but like for them, especially because there were piles of legacy code and they were used to it, like you just couldn't switch like that. Like, yeah, here's the important thing, that when you have a lot of legacy code, you just put new features in old code and it would all still work. And that was good enough for them.
I mean, there's probably going to be some inertia due to there being a team as well, but I wonder if, I mean, his team was actually just him, well, whereas other people working there would be doing something else, analyzing some other part of the data or something like that.
Sure, it would depend. And like he moved around, like, he was writing a lot of early Fortran at BC Hydro, but then later in his university career, he was also writing other ones. And so, yeah, you'd have to collaborate with other people there. But they didn't have like code didn't have project structures at the time. There was no Git or anything, so it was mostly just files that you would compile, and you'd have to invoke the compiler manually, and give all these compiler flags and linker flags and things. So there was definitely, I would say, a lot less structured software development, as we might call it today, and more just like making it happen because they needed to move on to something else. And instead of rewriting things, like, if it'd be much quicker to just dig up your old version of some code that you knew worked on a particular thing and tweak it for like a new problem. And so there'd often be like, you know, multiple versions of some file that you'd have laying around your computers. And he still has a lot of his old code, but some of it's been lost, you know, just from like, you know, moving from computer to computer, job to job, you know, like institute to institute or whatever, like things get lost. But they'd still do their best to reuse the legacy code rather than rewrite it, because they weren't programming for the sake of programming. Oh yeah, so here's a funny thing, is that when they were writing Fortran 66, Fortran 66 does not have if then else. And I was just trying to imagine, like, what the hell did you do when there wasn't if then else? Like, they had to wait until like the mid 70s until they had that magical breakthrough. Apparently they had like the ternary tests, like the three-way, like the C has those too. I think Python has them as well. Like they had that, but they didn't have if then else. So I think you had to use, like, what you would do instead is you would have clever go-tos. Like you'd have some like if statement that if it was true, it would like go to a lower line. Otherwise you would like do some like little tweaks or whatever right immediately below it. And then in Fortran 90 and 95, you got extensions for parallel programming. So this is really cool, because I'll show you later. But they're like, Fortran actually makes parallel programming kind of easy. For number crunching, I mean, like Go's stuff is probably more for like concurrent programming, whereas
I
Fortran
have a
is like,
question
okay, how
about
can we
the
do all this
previous.
matrix stuff in parallel? What's up?
I have a question about the previous slide. So did they have conditional jumps, like for the go-tos?
By conditional jump, you mean?
So like jump if such and such condition is true. Like,
Yeah,
like
you could
my
you could do like a simple test and then have a go-to statement after that.
yeah. Like what comes to mind for me is like in like an x86 process, you have like jump equal, jump not equal as like instructions.
Mm.
So yeah, that answers my question.
That's probably what the compiler would do, which is translate directly to that instruction.
Yeah, and as you saw in the other slides, like you had to mark the jump location specifically, like with those little numbers.
Yeah.
And you have to have everything. You had to have everything indented because go-tos were common. That's probably why C has them, is because Fortran had them. Like it's kind of all a shared legacy that's kind of in like paradigms and ideas passed from language to language to language. So our languages today like definitely aren't invented like in a vacuum. Like we're definitely building off of everything that happened before. And there are even some Haskell things that I noticed that like are in Fortran that like Haskell like must have gotten, or at least even just like terms that I wouldn't have thought were from that era, like existed, or like the concepts existed. He said that, like, you know, they weren't doing commercial programming Like it wasn't like like super serious stuff. Like no one was like, going to be following up on it. Like these things didn't typically lead to commercial stuff. A lot of it, like they'd be developing algorithms and then presenting that in a paper. It'd be like a method for determining some like chemical flow through some like media in the ground, and they'd describe a particular algorithm, and then they could demonstrate it in Fortran, and then other students or other researchers could take that, because there was no Git, right? Like back before like the days of the internet and Git, if you wanted to share code or an algorithm, you would do it through papers. So if you wanted to like oh, we need to find a technique for doing XYZ, it's like, oh, maybe someone wrote a paper, and you'd go and like you'd go through the literature and you'd find some algorithm described in some paper, and then you'd like copy that and you'd reference that in your paper. Like that was how you did kind of like the scientific software development at the time, and you probably still do in a way. He was telling me that like even today he still uses Fortran style, like Fortran 66 style comments and code alignment and stuff like that, which I thought was funny because you still can. The modern compilers will just take it. But yeah, one other point here is that they don't unleash programming languages on students anymore, engineering students, I mean. That they used to teach them BASIC or Fortran, but like if it's some numerical analysis thing, they just give them like some little MATLAB script because you can understand MATLAB in 4 seconds, and that's apparently like less stress for the it's like less to deal with for the engineering students who are already busy.
Did he have a strong opinion about not using pointers?
He didn't see the need. He had a colleague who did, and he told me that like, oh yeah, he had a colleague who was always like messing around with like the little fiddly stuff with that. But then basically the dad was saying it's like, if you can pass matrices around, like that's enough.
It would have been cool if he said something like, no, this is going to be too unsafe.
Well, and it is
We
too.
probably shouldn't go in that direction.
I didn't include those quotes. I had to cut a lot of the quotes, but one of them was about how you like before they had all the matrix the matrix primitives, that you'd have to set up your do loops really specifically, and that you could like very easily do buffer overruns, and so you have the same problem as C, right? That you just be like reading and writing like memory that wasn't yours, and there was nothing to protect you, and the runtime will just do it, and then you'll get out all this garbage data. And it was very easy to do, like off by ones, and suddenly you'd be off in like who knows what memory land you'd be in. Okay, so any questions about the history of Fortran? Otherwise, we'll jump into the language itself.
Don't think so.
Okay, I'll move on. Okay, so the extension that we use today for Fortran files is .f90, even if it's not like specifically Fortran 90. Before that, the extensions used to be .f or .4, and those would often be capitalized. But pretty much everything now is F90. If you use the Fortran package manager, which exists today, and you use it's like FPM new, it pumps out all the template files in like as F90, and that's just what you do.
Sounds like a fighter jet or something.
So Fortran. Fortran is strongly typed. None of that dynamic type wishy-washy duck type, none of that. We've got strong types here. Tell me, friends, what do you notice about this slide? What do you notice about the code here? What kind of stands out?
The bool has weird dots next to it.
What has
Oh,
weird
also
dots?
double colons.
For me, it's that the variables is a program.
Oh yeah, here, that's just the name of the program, so I could have named that anything. So like, let's just call it like...
Oh, okay.
It says implicit none, and I have no idea what that is.
Do Emacs. Do Emacs. Wait, what's happening? There we go. There. Oh, so yeah, you have to repeat the program name, like regardless of whatever the file, like your main file is called, the executable. Even then, you can rename the executable. Yeah, whatever. The program name is declared, and you have to end it at the bottom. Somebody said implicit none. I will explain what that means in a little bit.
Oh,
Can you have
types
programs
come
inside other
before the
programs?
names.
Can you have programs inside of the programs? Not as far as I'm aware. I think you can only have a single program block in like a group of files that you're trying to compile into a single executable. But you can have many
You could have
modules, and modules are like a newer thing for like modules are quite nice because you could have multiple modules in a single file, or yeah, in a single file even, kind of like Rust. And as long as they like are sitting somewhere in the file system, it like of the project, it all just comes together nicely. The module system was actually I was actually impressed by it. There was another question.
No, it's just a comment that the types come before the variable declaration names.
the assignment, yeah.
Correct.
Yeah.
So type is on the left and the name is on the right. And notice one thing that you cannot do. You have to declare all your variables first at the very top of the function, and then you can assign them values. You cannot have code up here. If I did, for instance, like print, if I did print star high doom, this would not compile. So you can't have like variable declarations interspersed like with logic. All your variables that you're using in a function have to come up top, and then you can set them to whatever you want in whatever order you want. But it's like at the very top, you're just like, nope, this is what we're using. So it's very clear. All the variables happen in one place. And you can't go like equals 1.1. I think you can, but it's bad. It does something that you don't expect. Anything else?
I noticed the dots on either side of true. I'm guessing that's like a keyword sort of thing.
Yeah, this is like it's a specific variable declaration thing. You can see here that a complex number. Oh, so complex numbers are a built-in type. Character. This says character, but it's both character and string. So you see that the type is character, but you'll see I've like declared it as I've like actually instantiated it as a full string. Booleans have dots around them, and complex numbers look like tuples. So this would be the real part, and that would be the imaginary part. Okay, we will move on. What could this implicit none mean? Loops. We're about a quarter of the way to Fortran Nirvana. Okay, so yeah, my dad always talks about do loops. He still calls that, like today, like to him, like loops are do loops. So if we're talking about even programming in general, he'll say do loops, even though do loops are specific to Fortran. So yeah, there's no such thing as a for loop. It's a do loop. So what you got here is sort of modern Fortran. So do, so notice that you have to declare the integer that, like the variable that you're using, you have to declare it before the loop. I equals, from 1 to 10. Pretty nice. Better than C's syntax, I would say. And it's looked like this since probably the 70s. So like by the 70s, actually no, since the 60s. So like I don't know what C screwed up, but like yeah, do loops have just always been clearer, I think. See this? Why is there a little star here? This is actually there are two other statements. One is like read and the other one's a write. And they similarly have stars in positions like that. That is declaring the output device. And when I say device, I mean it. Because today we just think it's like standard out and stuff. But back in the day, like it used to be to like other weird places. I think including files as well. But if you put star, I believe that's just sort of like standard out from from what the program is running in. But back in the day, that could be like anything. And back in the day, they might not have like had terminals. Like they wouldn't have been running these things on terminals if they were running them in punch cards, right? It would have been printing output to directly to a printer, like a line printer, like one of those like zzz, zzz, zzz printers, like a dot matrix printer. So that would have probably been some like keyword to say like to the printer. Another cool thing about the loops in Fortran is you can just make them concurrent for free. So this kind of feels like Go a little bit. So instead, you just go like do concurrent, and then it just works. And now, like you have to guarantee, in this case, you have to guarantee that like the results aren't clobbering each other, that the individual like things don't need each other, like previous, pardon me, successive like iterations don't depend on previous ones. If you can guarantee that, then you just get this parallel for free. Just by declaring it. So that's kind of cool. And it's been able to do that since the 90s. Okay, procedures. Fortran differentiates between functions and subroutines. Finally, we're going to learn what a subroutine is. For the Haskell-minded, functions are pure, like they're basically math functions, like you give it some input and you get some output. While subroutines are like these, like basically they return an IO unit. They're just meant for their effects. Let's see a subroutine. Okay, here we are printing a matrix. Go ahead.
First, can you go back just a little bit?
How did Fortran do the concurrency? What was the runtime like?
I believe that this says, it says concurrent, but I believe this is parallelization, not necessarily. Wait, pardon me. Is this parallelization? I believe you have to activate certain compiler flags to get like the full use of it, but I'm not sure exactly how it works. If you have multiple cores, they get used. I believe that's the. There are also some, I think in the newer Fortrans, there are also some like macro kind of things that you can slap onto here. I'm not exactly sure how they work, but you can tell like certain loops to be done concurrently, and the Intel Fortran compiler can auto parallelize code. So what it does is, as just like a part of the compilation pass, if it notices that, if you have the compiler flags activated, I mean, if it notices that certain code can just be done in parallel, it'll do it for you as part of compilation, which is pretty cool. Today, that might be like kind of related to SIMD or some vectorization and stuff like that. Is kind of a similar concept, but it was really revolutionary for the guys at the time. That yeah, if you were using the Intel compiler, just like your code could just be parallel for free without having to rewrite anything. Okay, let's look at the subroutine. Here we are printing a matrix. This is an example right from the Fortran site. You'll see that. See, here's a kind of a funny thing. We have our variables declared up here, like the parameters are here, n, m, and a, but then we're like declaring them again for some reason. So the types of your function parameters are declared inside of the function, not in the function signature, which is kind of cool. And you also have to add this intent in thing, which says that, which means it's like, oh, that is meant as like as a parameter coming in. It seems a little silly. And then like your normal variables are like immediately after that. There's some cool like data kind stuff kind of going on here for people with like Haskell eyes. You'll see that like we've got a variable coming in, and that's some number, and that's like an integer here, but then we're using that in a dimension statement. This is an array, right? So it's an array. So what this is an array A of type real, like the things in the array are real numbers, floats, but it has dimension n by m. So we're kind of like promoting these like we're getting these variables in, and then we're like promoting it to a type. It's kind of cool. And then we're just printing it, of course. And you'll notice that there's like no return value here. It's just doing the print statement, and then we're exiting. Functions, on the other hand, have a return value. Notice that we have no return statement here. Return is up here at the top. You put the variable that you want the return value to be, goes up here in a result keyword, and then you just have to set it somewhere in the function, and then you're good to go. Here we have some more like intent declarations. You set the result, and then there you go. So I guess it's kind of cool. It's like, okay, what are the inputs, and then what are the outputs, and it's all just right at the top. And then like, what's the type of, like, what's the return type? Well, you just have to look inside of the function in your variable block. You might think like, oh, that's dumb. I have to like look around for the type, but it can't be that bad because all of the variables have to be declared at the top anyway, so you know exactly where to look. So I guess your eyes would be trained to be like, norm, what's norm? And you just go, you'd look immediately there, and it wouldn't be a mystery. Functions can also be marked with the pure keyword, which forbids IO functions at compile time. That's true. Did that? Yeah. So here I've just got a quick little function. Let's just run that quick. So here we are using the new Fortran module. You can see this still?
Yeah.
Great, thank you. So here we've got a simple module and a simple little program. We are just calling the function, and then also I guess we can turn that off. We'll turn this off. So you can hear on the left, it's printing the number 1. Well, this is not a pure function, you'll see. So function good boy. We are declaring a number. We are, let's go num equals num plus 1. So we're actually doing some real like work in here. Okay, now it prints 2, right? But then we're printing the number, but then we're also returning the number, right? So it technically is a function. Like it's some mathematical function, right? Because it's actually got a return value, but we're printing it in there. And we're not printing it again down here. But watch this. I'll add the pure keyword and I'll try to compile it. I can't. Print statement at 1 not allowed within pure procedure. That's kind of cool. So you've kind of got these 3 things. You've got like functions, pure functions, and subroutines. And subroutines just seem to be for IO. But if you know that your function is going to be pure, you can declare it as such, and then the compiler will yell at you. I thought that was kind of neat.
Yeah. So it seems like that from what I thought was true, that turns out not being true, that like the distinction between functions and subroutines is that functions are pure and subroutines aren't. But it seems like pure functions are pure, subroutines are like only unpure, and functions are like both.
It's something like that. Yeah, it's experimentally that seems to be the truth. And this is nice because if you wanted to debug, you could just like really quickly like throw a little print in there and just like see what's going on. But then like for the actual full compiled thing, if you're like, no, this is a pure function, we are going to be pure. There's no like messing around. And probably that also has some compilation considerations, which is also true in Haskell, is like why you want functions, why you want to write as many functions as possible, like completely purely, is because like things can get inlined a lot easier. Whereas if there's IO in the function signature, like Haskell can't inline it, or as much anyway. Like the pure functions just are an excuse for the compiler to go wild with inlining. And I'm going to assume that Fortran will do the same thing. Like if you put pure here, it's like, oh, okay, now let's get to work.
Okay.
Does it also do any kind of automatic memoization, and do you know that kind of thing?
I don't know.
All right.
Sorry about that. And Fortran has structs too. They're called derived types. Here's a definition of one. Wait a minute. Why is that not highlighted? Maybe that's what's correct. Yeah, maybe that's what's correct. So here we are declaring a struct. Its name is tpair. It's got 2 fields in it. One's an integer, one's a real. And then here's us using it. So just as the same as before, our type is on the left. Because it's a struct, when we're declaring it here, like it has to be wrapped in type. For some reason, you can't just put like tpair and be done with it. Like you would think that that's what you'd be able to do, but you can't. You have to have like type around it to say that this is a user-defined type, I suppose. And here's the fun thing. Look at the field access. It looks like we're doing mods, but we're not. That is field access in Fortran. You can also define methods. Defining methods looks like this. You put like contains, and then you just have like a little function here. So it'll be like subroutine doom. end subroutine doom print Emacs. Then to call that, it would be like this: pair doom. That's what that would look like. So that's defining and calling a method. So it's like, okay, Fortran, thanks. You got structs, you got methods. What else you got? You got like cool concurrent. Oh, so that's basically the language actually. That's almost all there is to it. Like other than the specific, like learning the intrinsics and like learning like, you know, yeah, like what's built in stuff like that. That's basically what there is. There's not much more. There's not much more to it. What you've seen is like, yeah, most of the syntax and the basic stuff. Like it's not object oriented. Although I think the newer Fortran like adds stuff for that, and there's no exceptions. I don't think there's generics, which sucks. I'd have to double check that. So unfortunately, I don't think you can get cool ADTs or whatever. But for just like grinding out some code, like if we're doing like Go level code, this is kind of like enough, or like C level code. I can hear someone's mic.
That might be me. I was going to ask if you could actually like pass in the data type almost as if you were trying to manipulate the struct itself within the method call.
Do you mean like self?
Yeah, sort of like self. Exactly.
Yes, that's actually exactly what you do. You go like this. Self I. That's what that would look like. But you don't have to. You don't have to declare it. Like in Rust, you have to put a self there, right? You have to put self here. Like in Rust, it would look like that. Or if you're, yeah, typically it would be like that. But you don't here. It's implied. So yes, the methods do have access to the fields of the struct.
Are goto still commonplace in modern Fortran?
In my dad's code, probably. In Fortran, in like modern, no. I would say no.
Okay.
Hey, let's go find out. What's gonna happen if I go like 10 and then I go print hi, go to 10. No. Will this compile? Whoa, it works. Can you see how that worked?
Yeah.
So like it skipped no, like we don't see no there. So yeah, so goto is still recognized, but don't do it. Actually, I mean, even Golang has gotos, but don't do it if you're sane.
Yeah,
Does Rust have gotos?
I learned the pain of gotos after inheriting a very large SQL function.
Yes, I feel your pain. And actually, you know what? The reason why this still works is because of what I was saying before, is that like all Fortran still works. Like we're compiling in like Fortran 90 mode, but we can still just put normal Fortran in here. Like you can just put like Fortran 66 in here and it'll still compile. So therefore the go-tos, like all the old way of coding has to work still. It's like it's highly backwards compatible. And it's because Fortran is so like legacy code based that yeah, that's just how they did their technology. Like the old code must work. They were like dead set on not rewriting things.
So I'm guessing in modern Fortran you don't have to have 6 white spaces at the beginning of a line anymore?
You do not. No.
Because I
Modern
noticed
Fortran
that you
looks as
don't
what you
have
see
that.
here.
Yeah.
Yeah. Okay, so we got
Does
some time.
white
Go ahead.
space matter at all?
Does white space matter at all?
So, yeah.
Hold on. No, it doesn't.
What if you just
Okay.
completely unindent that entire program?
Yeah.
Will it even work inline? No way.
Wait, what?
It did not.
Yeah,
It did not work.
no. I just meant unindent, not inline.
Yeah.
Oh, you mean
just-
unindent? Oh, yeah. Pardon me.
Yeah,
Pardon
yeah.
me. Oh, yeah, that'll work. And the reason I know that will work is because I was refactoring some of my dad's old code that he wrote in like the 80s. I was reformatting to get it to like work, and it actually like was working. But
Okay.
if
Definitely less
you-
readable though.
Yeah, part of the fancy new Fortran module that somebody really cool wrote. It's integrated with the LSP, and it's also got the main like prettifier in there. So like you just don't have to think. Like I love having, you know, it'd be all uninlined. You just hit save and then it just works. Like
That's
I'm very
nice.
used to that now from Go and Rust. Like it's that's just part of life now. Apparently they even used to have those back in the day. That there used to be a thing called what did he call it? It was there was some prettifier that they had to run across the code like after the fact, but it would do the exact same thing.
For me, it was always just in Vim like GG capital V capital G equals, and then just
Oh, yeah.
reindent all the code.
Oh, gotcha. Nice.
Yeah. Emacs, old Emacs had stuff built in for this. Just automatic formatting.
According to the major mode.
Yeah.
Mm-hmm.
I can't remember if it was built in, but you used to be able to like define. I'm sure you still can, but you could define just rules for how to format everything
While we're
and
here,
just run it, and it would format it all for you.
I mean, today in Doom we've got CF, right?
Yeah. So just like as a reminder, we're like almost coming up on like an hour long for the talk. I don't necessarily know how much is left, but
Really?
you know.
Is that an hour? Oh, sorry. I'll go faster then.
Yeah.
Okay. Code is case insensitive, and the old comments you start with C, but now it's exclamation marks. So here's the dumb thing: is the types of variables used to be determined by what letter they start with. So to stop that, you use implicit none. So back in the day, you used to say like, if you wanted to get around monkey business, you could like redefine it. You could say like, okay, like variables from, let's start with like A to H or do whatever. They have this type. But like, that's why like if you had I or J, those would automatically be ints and everything else would be real. And that's why God is real, because God starts with G and G is from A to H. And so it's if you had a variable called God, it would automatically be a float. But it's considered, you're not supposed to do this. Like you're supposed to use implicit none so that there's none of that bullshit, and you're supposed to use explicit typing everywhere. Arrays are one based, so there is no like zero. You never have like a zero index of an array unless you define custom bounds. So you can actually have an array from like -5 to 5 if you use custom bounds. It's kind of a cool thing. Oops, what did I do there? So you have FPM now in modern Fortran, which is based on cargo. It's actually what we were using here. I'll just quickly show you manually. You can go like FPM run, and there it runs. If we delete the build file and we go FPM test, you'll see that it's pulling stuff down using git. Here it is. Like you can see all the compiler statements flying away, and then it runs some unit tests. And wow, isn't that great? Let's look at our TOML file. So here, like anybody who's familiar with Rust would be like, wow, that's just Rust. And here we are defining a dev dependency, which means that like it's only pulling it down for the test suite. But it's basically exactly the way that Rust works. And if you want to get rid of all those, you just delete the build folder again. FPM is very, very useful, and I'm going to teach my dad how to use it. Unit testing. I'll just show you really quick. So it's kind of what you would expect, right? So here we've got a module, and then we have a little program that's actually just running the tests. So vegetables is a unit testing framework. Here we are writing a test. Actually, here's like an actual test. So we got test function math. Result T is from the vegetables library. Here we are just like doing a little assert statement. And then here we are just like putting them together in the usual sort of unit testy way. So it's like, okay, we've got some like string statement that we want to say. And it's like, okay, just run this test. These ampersands. So, like in C or Go or Rust as well, like if you want to like end a line, but have it wrap, you put a backslash, but in Fortran, you put an ampersand. So these ampersands aren't functions. I thought they were for a while. It's like for formatting. Like if you do that, it'll go like that. If you do that, it'll go like this. So yeah, unit testing is fairly nice. It's straightforward. I found it more straightforward than Go. And you can, managing the dependencies is nice, because it's basically it's now like the Rust workflow is kind of like the Fortran workflow. Although probably not everybody's using this, right? Like the old neckbeards, they wouldn't know what to do here, but like I guess young guys would who like find themselves writing like Fortran for whatever reason would like love to be in this scenario. Libraries. So, wow, wouldn't you know? There's even an online ecosystem. We can search for a package. Let's go like command line. B-spline. Okay, look, flap. Okay, so there's a command line argument parser called flap. Bunch of MCLI, like there's a whole bunch of libraries, and they're like they're on like Fortran is using GitHub now. This guy is writing a ton of stuff. His name is Brad Richardson, and so when I was researching a number of libraries to use, like he had written like a number of them. So it's like there are like active people who are putting energy into like the Fortran ecosystem to make it to make it modern. And there's also, let's see, there should be a standard library around here too that they've got going on. It's somewhere in there, but actually, hold on, standard lib. So there's they've actually got like a community. They've got a community like managed like standard lib that they're working on. Like, of course, Fortran has built in what are called intrinsics, but I guess they're looking for more of a standard lib a la like Go's standard library. So I was surprised to learn all that, because from what my dad had told me, that basically my whole life is that it seemed just like this old crusty language that like nobody who wanted to do real work would use, or rather like our definition of real work was different, right? But I was like, no, like Fortran is a language that you could use for real software today, and like the workflow is not bad. And if you feel like doing some of that in Doom Emacs, now you can with the new module. Okay, thank you very much.
You said intrinsics there. I know intrinsics as like functions that map directly to CPU instructions. Do you mean something else?
It could be that. The way my dad was using it is that intrinsic means built-in function.
So it's probably the same thing.
Perhaps those map down to specific instructions. I'm not sure.
Yeah.
Okay, so well, first of all, let's all like give a hand to Foster.
Thanks very much.
Yeah. So nice. I assume no one else has any follow-up questions, because they didn't say. But
so that ampersand thing at the end of the line, that's basically like putting a backslash before a new line in shell.
Yes.
Just to confirm. Okay, cool.
Okay. So now it is time for Eat to talk to us about sitting inside of trees.
Yes, it is. Let me turn on my camera so that you can all see my ugly mug. Where's my camera? Oh, down here. I did not. Okay. I'm much closer than I expected. Okay. Oh, that's a nice touch.
I can't hear Yeet anymore.
Yeah, he just
Yeet has yeeted himself.
Right after he said, "Oh, that's nice," and then
it was probably a button that he wanted to press for a long time.
You around?
Can he not hear us either?
Where did he go?
He yeeted out of here.
Is he in the isolated
in the Discord?
speaking zone?
Oh yeah, he's like on an isolated area there, right?
I think that's the platform to like present.
No.
I think that makes it so you
Yeah.
can be heard everywhere. Oh,
Is
Oh,
my connection bad?
There we go. We got him.
there we go. Now
there
yeah,
we
it's
go.
fixed. And now we can see the slides too.
Am I back?
Yes.
Yeah.
Okay.
Hey, streamer, your camera is pointing upwards again.
I can see up your nose.
I apologize.
That's wonderful.
I'm using I like my screen at a certain angle, and I forget my webcam is also attached to my screen. Eventually, when the streamer bucks start coming in, I'll have to upgrade that. But yeah, so before I was rudely interrupted by my internet, I was discussing what is tree sitter. Well, the definition, not the definition, but tree sitter is a parser generator and incremental parsing library that allows programs to become syntax aware of the programming language they are editing. That's a lot of words. What does that mean? So let's just break that down. So let's start off with parser generation. Essentially, a parser generator, for those who don't know, is a context-free. A parser generator takes in a context-free grammar representation of some code and then generates some object that can be used for parsing. So in a higher level language, something like Python or Racket, that would be a parser function. But in TreeSitter's case, that will be a actual shared library. In this case, TreeSitter's grammars are written as a JavaScript object, which are then compiled down into a C file, which is then compiled down into a parser, which is then compiled down into a shared library. Here I've got an example of a very simple grammar. So essentially all we're doing is we're exporting this, the product of this grammar function. We declare the name of our language. So usually that would be the name of the language, so Ruby or something. And then we have an object which contains our rules. These rules can be self-referential and recursive using this dollar variable that is implicit to the grammar function. Essentially, you can get any value and you can recursively get values. So here I'm declaring my top level, which is my source file. This is like the root of my tree. And my source file can contain basically this subtree. In this case, it is called hello. And then hello is just the string hello Rigor, because he's always saying hello.
I think you're pointing to stuff.
It's a little bit more complicated than this example, of course. There are functions that allow you to do things like have a sequence of nodes. So you can have, to define a function, for example, you would define it as a sequence of the function keyword, the name, an argument list, and then the body.
Are you on the right slide?
I should be.
Okay.
It should have the grammar on it.
Yes.
Yeah.
We still see parser generation. Is that?
I would have pulled up a better example, but I was doing this at 2 a.m. So.
Yeet, can you hear me?
Yeah. Yes, I'm still on parser generation.
Okay. Good.
Yeah.
Hello, Yeet.
So.
Yeet. Can you hear
for
me?
example, you could basically you can use a lot of JavaScript's facilities for this, and this will just be compiled down into some. Yeah.
I think you can't hear.
Is something going wrong?
Rigor's trying to connect with you.
I'm okay, thank you. I'm not sure if I'm still breaking up. Can people hear me all right? Yeah, we can hear you.
Yeah, but
Okay.
it seems that for whatever reason
Yeah,
specifically,
so essentially you would use a sec function, and you would specify some list of arguments. You could use a choice function to say that, it can be either this or this. And if I would bring up a better example if I had one. Maybe at the end, I'll bring one up. But that is essentially what parser generation is. It will take this JavaScript file and compile it down into this shared library, which we can then use in incremental parsing. So with this parser now generated, we can now do some cool stuff. I will not be going into a lot of detail about how, again, maybe at the end, but in essence, it starts off by passing the tree like any other thing, any other tree parser, any other AST parser thing. It uses a generalized form of LR parsing, which allows it to sort of sort out ambiguity. So essentially, you could have a parameterized state. If we take, for example, JavaScript, if I switch over to something else, how do I switch? Did I just turn off my screen share? I think I did. Yeah.
Yes, you
So
did.
if I switch over to, let's say, let's just go over to, yeah. Well, let me open up a quick JavaScript file. Let me just create a new buffer. That's not what I wanted to do. Test.js. So if, for example, you had some ambiguous statements, so I could say y equals parameterized x. This is valid JavaScript. I don't know why you would want to do this, but you could. The problem is, in JavaScript, there is another way to use this. So you could say something like z equals an arrow function of some kind. So arg, and then hi. Sure. It doesn't matter. So the problem is with a regular LR parser, as you go across, it will pass this as a parameterized expression, and it will not be able to deal with this sort of arrow function case. As TreeSetter needs to handle this case, what it does is it will actually fork the tree. So instead of having just sort of async, I shouldn't have gone into detail. Essentially, it can handle ambiguity quite well. If I had a diagram, it would be much clearer. But anyway, you can see that I haven't really revised this talk. Yeah. Anyway, so this, yeah. So anyway, so it allows us to deal with ambiguity as well as handling errors in a similar way. It will fork essentially the stack and deal with the two cases individually, and the case that succeeds the most will be sort of pushed onto the sort of the compile stack. Now the nice thing about TreeSet, but the thing is, after this sort of first pass, it doesn't need to recompile the entire tree unless you change your entire file. Instead, what it will do is it will walk for all affected nodes. So for example, so instead of having to change the entire tree, it can only change the affected nodes. My voice cut. So after the first pass, it does not need to repass the entire tree. Instead, it will walk the tree for all affected nodes. So let's say I change that first parameterized expression in the first example to an arrow function. It does not need to touch the other affected nodes. This is unlike other passes in other text editors, like something like PyCharm, where it would have to repass the entire tree, which is quite slow. So in that case, that's what makes it really cool and also really bloody fast. Now, of course, all of this is really quite cool, but why should you care? Well, there are many reasons, one of which, probably the overarching reason, is we now have an AST to play with, an abstract syntax tree. This allows us to play with our code structurally and manipulate it in terms of functions, statements, and expressions, which is something historically was only a privilege only Lisp had. So let's just talk about what that actually looks like. So I'm now going to switch over. I'm now going to switch over to my editor real quick. I've got some Ruby code that I use for pretty much all my demonstrations. I've been meaning to release it, but I have to basically remove, it was some coursework, so I have to remove some of my write-up for it. Where is it? Not test.js. It is this one. Yeah. So hopefully people can see that.
Yes.
So first off, let's start off with
Control plus.
syntax highlighting. If I turn off tree, okay, tree setter
You
icon
could
type.
zoom in a little bit.
I think you dropped
Oh no.
again.
Ooh,
it's
now,
connected
now he's
again.
dead.
He only needs to write HL. I did it a million times. He wants to do MX3 seater HL mode.
But that's fine. Yeah, I think Emacs has crashed. I think the first thing people notice is that method calls are no longer highlighted. So in this case, if you look at the function char split, the method char split, the split call within it is actually not highlighted anymore, while before it was. If you look down at the bottom, I think, yeah, Emacs has crashed for me. I think I've got to force quit it. Give me a minute. Don't you love technology? Why am I starting the daemon again? Should have just started a regular Emacs session. Yeah, so basically because we are allowed to play with the thing. What am I actually sharing? I don't actually know. This is going so smoothly. Okay. I think we've crashed again. Okay, we haven't crashed again. No, okay, I don't particularly care. I think it's because I'm trying to stream as well. Not stream, video call. Yeah, so back to what I was saying. Traditionally, things like method calls and method and function calls are not necessarily highlighted, because when you have a regex-based system, like Emacs has with font lock, you will end up losing a lot of that. You won't be able to necessarily get a regex specific enough to highlight those things. But in tree setter's case, we don't actually need to worry about that, as it doesn't need to use regular expressions, but it knows the code structurally. So, for example, down here with this instructions.length, the instruction before the length was not highlighted. It did not know it was a method call, so it was just white. But now we actually are calling the length method on this object, and it's actually highlighted and quite nicely. I think the difference is quite stark when we compare it to something in Python. So if I go to some dinky little Secret Santa program I wrote, give it a minute. My LSP Python for me is quite slow. I think.
In the meantime, I kind of have a question. Does tree sitter know what
poetry is all giving me errors? But if I were to do
wait, can you hear me?
Tree. There we go. If I were to turn that off, you can see that it.
Monad, what did you ask? Maybe I can answer. Hello? Am I disconnected as well?
No, I can hear you.
No, you're allowed, Marco. Yeah.
No, we can all hear the eatless people. You just can't hear us.
Yeah, you can't hear.
Highlight
too.
Hit. Yeah.
He's still going.
this-
He doesn't know.
Hey,
Wait,
the
By
video
the way,
came
Heat,
back.
we
What's
couldn't
happening?
hear you for the last minute.
Someone. Yeah.
Okay. So how long have I been out? Where did I leave off?
The last bit
30
I
seconds.
heard
When
was when you were
Emacs
talking about
crashed.
the coloring on the length function.
Okay.
Yeah, Python is
Basically,
slow.
syntax. Yeah. Okay. So basically, syntax highlighting is better. That's what I was trying to get at. If I turn on highlighting, you can see instantly that it is so much better. Like arguments within our function are actually highlighted as arguments. Method calls are highlighted as method calls. In this, keywords are highlighted better and whatnot. It's
Yeah.
just better, more colorful, much easier to pass with our eyes. But what I was trying, after I was rudely interrupted by my internet again, I started talking about structural text objects. So now, because of Tree Sitter, we now have an understanding of our code. So if I were to pull up something like the Tree Sitter playground mode, something I'm working on, really the tree that Tree Sitter presents. And because of this tree, we can do things like highlight within a function. So I can yank the contents of this function quite easily. I guess I could just visualize that, and I didn't need to think about that at all. If I wasn't using structural text objects, I would have to highlight. To get this highlighting, I would have to use line numbers, so like v 6 lines or what have you. But here I can just say v in function, or yank in function, or change in function. It very much fits in with our way of thinking, but it's now much more structural. And this extends to other things. So if I had a class in this file, I'll be able to highlight, I would be able to get the contents of a class. Let's say I want to change the arguments in this argument expression. This function method call. I could do change in function call, which is bound to F bound to F, and then I could just type in whatever I want to. The same works for function calls. Change in function. No, sorry. Change in function, and I can rewrite this function without having to worry about that. Out of the box with the new tree sitter module, we get quite a few functions as provided by the README. So if I were to pull up the README for the module, out of the box we get function calls, class comments, conditional, so that's your if statements and loops. Now, I of course want to get more, but that is sort of like the main sort of all of them. I think, yeah. So, next up, I was going to talk about this actual sort of the actual tree. Now, the actual tree itself is not terribly useful to everyday programming. But what I'm trying to do, what I've been developing for the past couple of days, well, weeks, is this sort of simple playground. Essentially, it's, if we compare it to the debug mode that comes out of I would say that my playground is a little bit nicer to look at. We've got these simple jump buttons, which allow us to basically highlight the subtree at this point. So if I wanted to, let's say, highlight this comment here, it would know exactly what I'm talking about, and it will actually jump to the buffer and highlight that. That's also a feature in the playground. So if I were to exit this, play. I think Emacs has crashed again. Whenever I do too much, Emacs crashes on me. It's
F in the chat, guys.
give it a minute. Oh, isn't this fun? I think I'll have to, I'm just gonna, yeah, I'm just gonna go back to my, oh wait, hold on, is it back? Can I do stuff? Hello? Okay. I don't want to quit Emacs. No, it's still crashing. Fun. Anyway, so of course there is the playground, and there is it's stuff is happening. Can I type? I can't. Okay, I give up. Let's just go back to my slides. Actually, let me just share my entire screen. No, let's not share my entire screen actually. Which one is it? There. Yeah. So after this, I would have shown you like structural folding. Folding is not necessarily something that I have a good example for, but it is better, and I think much more importantly, easier to extend because of Tree-Sitter's query language, something I'll probably show you after I turn off my browser. And I think one of the coolest things that is sort of still being developed is Lispy-like editing for code. A package called tree edit is actually trying to bring Lispy-like editing, sort of not only the slurp and bar functions you're sort of familiar with, where you sort of take in a value into a higher construct and then sort of remove a lower construct from a higher one, slurping and barfing. It is also allowing you to edit the ast structurally, which is really quite cool. So what's next for the module? Well, at the moment, the module is quite complete. Everybody can sort of use it now. Everybody can use it now, and they will have a great time, for the most part. Unless you're Marco with a text object already bound to some other place. I will get to that hopefully today. I think there are a couple of bugs that need to be ironed out, but other than that, and I want to include the playground into this first release. But other than that, the module is pretty complete. Eventually, when tree edit and combobulate, that's sort of another package in a similar vein to a Lispy-like editing experience for other languages. Once those are a little bit more feature complete, I'll probably add those to the module as well. I will add those to the module as well. But yeah. Another thing that I think you guys can also help out with is language support. At the moment, Tree-Sitter, if I were to go to github.com, Emacs Tree-Sitter Langs. I think for the most of the mainstream languages are here. But the thing is, there is not a lot of, a lot of the main languages are here. So if you just program in Rust and Python, for the most part, you're going to have a great time. But if you were to code in something like Julia, while the parser is in the Tree-Sitter Lang repository, it doesn't have syntax highlighting just yet, because it needs an actual highlights file. So I guess while I'm here, I might as well show you what queries look like. So if we were to look at something like, so C has a highlights.scm, and this is essentially a query file that associates certain structures with certain what are known as match clauses. So here we've got a choice. So any of these are basically called a keyword. And then this query, basically you can have a storage class specifier or a type qualifier, also qualify for a query. These are sort of nodes within the tree. And basically you write out this file, and what Tree-Sitter will do is will associate these words with some sort of font face, sort of like how FontLock does it with regular expressions, but faster and much more structural. So this is something that I think, while it's not necessarily terribly difficult to do. So if you do see something missing, then feel free to add it. I think for the structural text objects, that is going to be in the nvim project. The way that's sort of framed is, so if I go to github.com and nvim Tree-Sitter, there. not a lot of objects have full coverage of all the text objects. So if we scroll down, they actually generate a nice sort of a nice sort of coverage chart for this. So Bash doesn't have, for example, block.inner and block.outer text objects. Those need to be written in. C# has pretty good coverage, and so does Rust and Python. Of course, Go will also have it. Julia also has good coverage, which is why I want to sort of get it up to spec. Ruby also has great coverage, mostly. And yeah, it is so. Yeah, so if you do see something missing, then do feel free to like PR, mvim tree sitters. That's what. So the actual evil tree sitter text objects package actually pulls these queries. So both benefit from this work. Yeah. Then there is also, so other than that, I talked about tree edit, and then yeah. Other than that, there are some other cool resources here. So there is a talk by Ethan Laber on tree edit itself, giving a much more detailed example of how it actually works instead of my sort of ramblings. Then there is a strange loop talk by Max
By the way,
Brunswick, I think.
you're still sharing the GitHub window, not the presentation.
That's fine. I'm pretty much done with my slides. I don't really have. I'm just saying these things. I'll link to all of these in the Discord, so don't feel like you don't have to go hunting for them. But there is the strange loop talk on how tree sitter actually works. The algorithms they use. It's a wonderful talk, very well structured, and has lots of diagrams and nice things like that. And then if you want to know how actually Emacs tree sitter works, then there is a Emacs Conf talk by the man himself, Ublont, who talks about Emacs tree sitter. And yeah, that's really all I have. Are there any questions about that? About tree sitter? Any sort of yeah?
So
Can you hear
if
me
you
now?
Oh,
Go ahead, Nano.
okay. So my question is, if you were to define custom syntax in something like a Lisp or something, like what comes to mind for me is Racket, because that's what I've been learning. How likely is custom syntax to break tree sitter?
So one thing I didn't really discuss was error handling. So if I were to like switch back to Emacs, hopefully things are going to work out now. Which one is it? There. Allow. What I didn't really show was error reporting within tree sitter. So if I were to open up the playground, and let's say I wanted to put in some invalid syntax. What happens is down here is it will actually show an error between these ranges, and then it will still try to parse the tree as best it can. Now, of course, that is not necessarily practical for something like Racket. I think Racket itself is so broad, like it can have any syntax, and at that point, I don't think there is anything you can really do to sort of. There is no context-free representation of any language.
Yeah, like
possible. Nothing that's useful. So
yeah,
it's yeah. So
I
for Racket,
completely
especially
agree
when you're
that
defining your own DSLs, I don't think that's possible. But for
sorry. Yeah, so what I was going to say is I understand that like the custom syntax obviously wouldn't have the syntax highlighting expected by tree sitter. Is more a question about would it just break tree sitter, or will it sort of like handle it somewhat gracefully, even though it won't highlight that part? Which it seems to be the answer is probably yes.
Yeah. You sort of cut off like through the first part of your question.
Oh yeah, so it was just
Nano.
yeah, so I was just asking, like, obviously if you define custom syntax, it won't be able to highlight that because it doesn't know what it is. But I was just wondering, would it just break, or will it sort of handle it somewhat
Oh.
gracefully?
Yeah, so that's what I was trying to show here. So yeah, it will so for example, let's say I put in some invalid Python syntax, something a bit smaller. So if x do y, and if I were to have a look at the error that was generated, I don't know why I tried to do a new example here. So first of all, so for what I did was I just removed the colon, making this syntax invalid. But as you notice, the rest of the tree is unaffected. All tree sitter does, because of its sort of generalized parsing, it can handle that gracefully. So it will show an error node, something that I plan on highlighting slightly differently. But then it will still try and parse the subtree, so it's still highlighting the identifier, it's still highlighting the expression statement, and so on and so forth. It's handling it somewhat gracefully. And that's sort of quite nice. If I were to include something like a Python match statement, something that's not handled by Python mode or the tree sitter parser at the moment, match x case x, sure. Format all is annoying. If we were to go down here, it probably won't highlight it. It will not highlight it necessarily correctly, but it won't also break the entire tree, which is really quite handy and really quite helpful. Because we don't want to have to necessarily break the entire tree every time we type something. Yeah. Hopefully that answers your question.
Yeah, that does.
Somewhat.
Okay.
Yeah.
Yeet. Rigor was
were there
asking.
any other questions on that?
Hello.
Yeah.
Yeet. Rigor was asking
Somebody
if you could
talking?
get
Am I breaking?
nested languages. So, for instance, get highlighting of SQL queries inside of strings inside a different language.
I don't think I can hear. Can people
you hear
me?
We can hear you. Can you hear?
Yeah.
Can you hear us? Or can you at least hear me?
Yeah, I can hear you. I can't hear Bond.
Okay, I can repeat
think
the
Bond
question.
is trying
I
to
can repeat
speak.
the question. Yeah. So
No.
Yeah.
so he was repeating Rigger's question, which is, can tree sitter handle nested languages, for example, like SQL inside a string for something like SQLite or something, I'm guessing, or maybe even other things.
So that would be down to the parser itself. So if the parser implemented a SQL DSL, or even just imported the SQL library, one of the benefits of using JavaScript is that you can import other grammars. The purpose he sort of brought it up was for defining sort of the C++ grammar in terms of the C grammar, or the TypeScript grammar in terms of the JavaScript grammar. But if you wanted to have like a nested language, you would have to include that in the parser itself, which is not necessarily that great, but it is possible. So yeah.
Cool.
So if there was, yeah. If you want, you can also put questions in the Discord. I have view of that, so yeah. Yeah, but I can't hear anybody. I think it's because I'm sharing my screen. Maybe if I come down to this area.
Okay, wait, can you hear me?
Can I hear people now?
That thing that you can do.
Can you
No, I
hear
can't.
us? No.
Wait, how do you know if you can't?
What?
Hold on. Can I hear people?
We've been faking this.
Just
whole time.
No,
ignoring
I
us.
can't. I
You can
literally
hear me. You
hear
could hear
us,
me
but-
before. You could hear me before. Can you hear me
I can
now?
hear you, but I can't hear anyone else.
Okay, now
Uh,
as the translate, tell Yeet to try and disconnect.
I'll stop sharing my screen.
Because
This is very weird.
So
I might have to
does
come
it have
back.
something to do with the fact that, like, I don't know if that's just on my screen, but on my screen, when I look at your face cam, it has my portrait in the corner. Is that the same for everyone else, or is that
Yeah,
anything to do with is that why you can only hear me?
No, isn't that his?
I
That's his
have
portrait,
no
not
idea.
yours.
I
Oh, does
I
he have?
think it might be.
Melo has
Oh no, it
figured
is.
out.
It just has a similar one. Never mind.
Yeah,
Oh, no.
it's just a similar one.
Never mind.
Sounded so good as a theory.
Well, anyway, if people want to put, I think something's happening. Where am I? Oh, I'm
Okay,
on
well,
Monad's screen.
I think we're transitioning to the next talk now. Anyway.
Yeah. Okay. Wait. Let's just. Okay. Yeah. Let's give each a moment to maybe I don't
So
know,
that
like
you can hear as well.
reconnect or something.
Yeah.
And then we might talk.
Yeah. When he comes back, give him a hand as
Can
well.
we do a sound check, by the way?
Can we do what? Yeah.
A
Okay.
sound check.
Yeah. So presumably everyone can hear me.
Hello, Monad. Can you hear me?
Yeah. No, we can hear you.
Yes, finally. Yes,
No,
Monad.
everyone can always hear everyone. It was a Yeet problem. Yeet did not hear us, but everyone heard the thing. It's why the recording is going to be really funny. Yeah. Okay. So, okay. Wait. Hold on. I'll type in the. Okay. I'm not seeing anyone in the Discord that says that they can't hear me. So hopefully we're good on that front.
Well, technically, if they didn't hear you, they wouldn't be able to hear you ask if they can hear you.
Yeah.
So they wouldn't say anything. But no, I think it's fine. I think it's fine.
They can just watch the recording afterwards.
Yeah.
That's true. That's true.
Okay, so all right, so let's give you a moment to reconnect. I can hear someone in the back.
Yes, I'm back. Yeah.
Okay, can you hear me?
I can hear you. I think I was just.
Hey.
Incredible. We have solved the
so-
problem. Okay.
Eureka.
So yeah. Okay. So hi, I'm Monad. Welcome to Relativity for Non-Physics. Just as a structural note, because like sometimes physics questions are kind of long and complicated. If you have one that you want to ask in the middle, type it in the Discord. I will be looking at it. But during the talk, I will stop for questions and like checks that we're all like doing okay in the middle. So at that point, feel free to come up on voice. Also, I'm going to do my best to speak slowly. I talk really fast. It's a problem in my day-to-day life. So do tell me if I'm going too fast. Like honestly, I need it. I don't want to like jabber on and lose everyone in the process. Okay. So yeah. So here are the goals of this talk. I want you to come out of this talk with at least a better understanding of three things. The first is the importance of symmetry in physics. The second is the fact that there is a universal speed limit, and that this is, in essence, what relativity is. And the third is that once you talk about relativity, there is no such thing as universal time. Each point in the universe, each person functionally has their own clock that might be running at a different rate. Oh, and also when you write questions in the Discord, like at me, so it's highlighted. Yeah. Okay. Good. So before we get into the talk, like a bit of like things that hopefully you do know and some backgrounds. No, yeah, there is a universal police. It's called the symmetry, basically. Yeah, okay. So here's some math that I really hope that you know. If you do, it will make the talk a lot easier. If not, hopefully you'll still be able to get some stuff out of it. So the first is like basic arithmetic. Hopefully everyone knows that. Everyone knows what trigonometry is, stuff like that. Two, it would really help if you know what derivatives are. If you don't, the derivative is basically the rate of change in a function. So the derivative of your location as a function of time is your velocity, because that is how fast you change your location. Third, it would generally help a bit if you know what a group is. If you don't, a group is basically a set of transformations. The intuitive example is like rotations that you can do on like a sphere or something. And if you rotate something twice, you still get another rotation. If you rotate something, you can rotate it back and get back where you started. There is the identity rotation that doesn't do anything. There is associativity that doesn't have an intuitive explanation and doesn't really matter. So yeah. And also, it would be cool if you know some basic linear algebra, mainly matrix multiplication. If not, again, not super big deal, but it'll help. Okay. So the first concept I want to make sure that we all understand is what a coordinate system is. When we talk about physics, we want to describe the world around us. And in order to do that, we need to know where things are and when things are. These are basically like all of like our understanding of physics basically rests on the idea of like knowing where things are, right? Generally, in non-relativistic terms, we work under the assumption that that time is some sort of like universal parameter running in the background. So what we actually want to do is calculate like our location functions as a function of time. Basically, the goal of physics is to calculate these three functions. If we know what these functions are for every particle in the universe, we can basically go home. We have solved physics. We know everything. Now, it's important to note that X, Y, and Z are not special. Like they are like when X, they're like up, right, and forward. They're just directions that we can choose to parameterize all of our points in 3D space. We can just as well use like spherical coordinates. We pick a point of origin. We have the distance from that point and our angles and stuff like that. And that is like a totally valid description of the universe. So given the fact that and in theory, any like three functions that give each point in space like a unique value that we can like parameterize them, because we need three. We can actually, I'm pretty sure we need three. There's like this thing where you can do like a space filling curve, but I don't remember if that's actually usable in real. Well, no, you can. Like you can even use one, but in reality, you use three. And that's a topic for another day. But basically, any way in which you parameterize space is going to be valid. But the problem is that like if you use like a really weirdly convoluted parameterization, your description in physics is going to be your description of physics is going to be like really hard to work with. Generally, we want to choose a description that makes the world simple. Like for example, you could choose a coordinate system where once you go into Britain, all of the distances are now like 10 times as long. And every time you go in and out of Britain, you need to remember to account for this difference. And that would be like a valid description. Maybe this might be me talking slow. I'm not sure. I can go a lot faster. I'm trying not to. Okay, but whenever you would go into Britain, whenever you would go to Britain, you would have to account for the differences, and that would be like a huge headache. So yeah, you're right. I need to stop. I'm now having the huge problem of having chat open and being distracted. It's really bad. I'm gonna have it farther away, so when I'm looking at my notes, I'm not accidentally also looking at that. Right. Okay. So yeah. So we want to choose a coordinate system that makes physics easy to describe. And the way that we generally do this is by choosing what we call by working in an inertial reference frame. Generally, when we talk about physics, we want to have like a coherent description of physics. And we can also talk about a slightly different coordinate system where physics is still the same. The easiest example for this is if you do an experiment and you do an experiment tomorrow, everything else being the same, you should get the same result, right? Without this, physics is basically pointless because we can never predict anything. This means that our coordinate system has a symmetry to translation in time. So moving from a coordinate system where t is what we have now, and t is just the same, but plus 1 day, which means that basically the coordinate system of doing the experiment tomorrow. If physics is symmetric to this transformation, then we say that both of these are inertial reference frames because they preserve physics. You can do physics outside of inertial reference frame, but then you need to remember to account for all of the added stuff, like for the weird distance things happen at the border of Britain in the previous example. I also want to talk for a moment about just some notation that is going to make our lives a bit easier. Generally, relativity works with what we call 4 vectors. They have this little mu index. But we're going to represent them as tall vectors here. We do this generally because when you talk about points in space-time, we want to talk about where a point is in space and where it is in time at the same time, because that is going to be really important. But also, for the most part, in order to understand things, we don't really need 3 spatial dimensions. So all of our actual calculations we're going to do with 1 time dimension and 1 space dimension. Okay. Are there any questions about the background?
Can I ask a silly question?
Yeah. What's up?
So in the previous slide, you kind of defined what it meant for something to be an inertial reference frame, but I guess the word inertia is related to the word inertia as we know it otherwise, right?
Yeah, pretty much. That's a good connection. I will make note of that later when I go into symmetries, but that has to do with this.
Okay.
Okay.
What is
So
CT?
yeah. What?
What was CT?
Right. Yeah. No. Good point. Generally, in relativity, because we want our time units and our space we want to like measure time and space with the same units. So we measure time in c times t, where c is the speed of light. Because time is speed and time is in seconds and speed is in meters over seconds, CT has units of meters. So because of that, we generally want to talk about CT. What you do in an actual relativity course is that you choose your units in such a way that C equals 1. And then you can measure time in meters or space in seconds if you want. But I'm trying to keep the technical like notation jumbo to a minimum here. So I'm not going to do that. But in real life, people that don't do this are insane, and they do, and I hate them. But yeah. So okay. So symmetries are really important. They are so important that they functionally determine what physical theories we are even allowed to have. When I talk about physical theories, what I mean is things like gravity or electromagnetism. What I mean is things like gravity or electromagnetism or even like hydrodynamics or whatever. These are things where like we have a model for like how like particles in the universe generate forces, right? Like the law of gravity, like F equals G m1 m2 over r squared, if anyone knows that. So if we think about physical theories like this, Newtonian mechanics is less of a physical theory and more of a framework. Because like Newtonian mechanics tells us in what way do we need to structure our physical theory for it to make sense in the universe. So it is like a thing that we slot theories into. Yeah. So the question is, if we want to like truly understand how Newtonian mechanics works, we need to ask what are the symmetries that Newtonian mechanics preserves. Because wait, okay, clarification question: is it clear what I mean when I say that physics preserves a symmetry, or
No.
okay? So if you remember the previous example that I had, that generally we assume that if we do an experiment today and we do an experiment tomorrow, we keep everything else the same. We will do the same. We will have the same experiment because physics today and physics tomorrow is the same. This means that our theory is symmetric to translations in time. Similarly, in the next example, I will tell you exactly what I will have. Okay, no, actually, yeah. But is that clear? Did that help?
Kind of.
Okay, because like
I'll listen along, and if it doesn't make sense still down the road, I'll bring it back up again.
Okay. Because an easy way to think about this is that a circle, for example, is symmetric to rotations. You rotate a circle, it looks exactly the same. A square isn't. If you rotate it by like 3 degrees, you get something different, right? So it's not symmetric.
That makes sense.
Yeah. Okay. So what are the symmetries that Newtonian mechanics preserve? Well, in order to answer that, we need to ask ourselves, what are Newton's laws? Because they basically define Newtonian mechanics to an extent. So first law, with no outside forces, objects move at a constant velocity. There is an element of like begging the questions with what is an outside force, but basically assuming that we model our universe with a bunch of like individual things that have a meaningful existence on their own, like particles in space, and they affect each other in some way, then if we have one particle alone in space that isn't interacting with anything else, what is it going to do? And the answer is that we assume that it is going to move at a constant velocity. Its location as a function of time is going to be some sort of straight line. If it's standing still, then a equals 0, and it's just going to stay put. And if it's moving, it's going to move at a constant speed. So the relevant question is, yeah. So the thing is that we want to ask ourselves, okay, if the concept of not having outside forces makes sense, then this has to like stay after we move to a different inertial reference frame. Because no matter what way we would describe physics, we still have to assume that there are no outside forces. So in our definition, the reason I'm using a for velocity, it's because the important thing is that this is a straight line. And yeah, a is acceleration, whatever. This is a linear equation. You should be able to deal with it. I'm also using b and not x naught. Okay, so like it's fine. Yeah. So the question is, what types of symmetries preserve straight lines? And here, and here is the answer. Okay. Oh, right. Also, like if we do this in 3D space, then everything is the same. We just make everything vectors, but that's kind of neither here nor there. So what symmetries preserve straight lines? The first one, which I already talked about, is translation in time. If we change our time coordinate to be t plus some other time t0, then actually, I mean, in retrospect, maybe it would have been better to show how this preserves it, but also maybe keeping the math to a minimum. But basically, this the resulting function of the function of t prime is still going to be a straight line, just a slightly different one. Similarly, translations in space. This is just if we plug this in and like move the things around, we're still going to get a straight line. This is really obvious if you think about it visually. Like moving in time is just going to move like the line up or down if you have like t as like the time axis at the bottom of the function. And in space, we're just going to like move the line in like different directions. Another thing is rotations. When O is some sort of like orthogonal matrix, or again, you can visualize it, you can move the line around. This preserves a straight line. And also, if you change your coordinates to move at a constant speed, this basically changes the angle of the line. So this is a set of transformations that preserve what straight lines are, and we call these Galilean transformations because I think Galileo figured some of this stuff out. I'm not sure. Also, I think I spelled Galilean wrong here, but maybe not. I'm not sure. I think there's like more else. And for the math fans in the audience, this is of course a group. It's called the Galilean group. It sucks. It's not a pretty group, but it is how we thought the world worked before Einstein came along, right? So what we understand is that this is a set of symmetries that we have for Newtonian mechanics. Yeah. Okay. So this, of course, so now we want to ask ourselves, well, what happens when you use some other transformation? Like you say that physics doesn't stay the same. How does this change? How does this matter? And the good news is that you all already intuitively know the answer because you've been in a car before. when you drive a car at a constant speed, you feel like some bumps out of the road, but generally you feel like you're like in a jittery room, but it's a normal room. But when you brake, you can feel yourself get smushed against the chair because now you're in an accelerating reference frame. When you brake, you aren't at a constant speed. You're slowing down from some speed 100 kph to 0. And when that happens, physics changes because suddenly every object in the universe in an accelerating reference frame gets pushed back at all times. And you can do physics with having like this constant acceleration on everyone at all times, but you don't want to because it's annoying and you don't want to deal with it. This is why we formulate physics in an inertial reference frame. Okay, so this is why it's important to stay in the frame where physics is the same and you don't have to deal with extra stuff. Also, we have Newton's second law, which is F equals ma. This has interesting implications about things like the starting information we need to predict stuff about the universe. But the important thing is that F is where our forces come in. Like our physics in general in the Newtonian framework, knowing what where we put the theory is in the value of F. And here we see that F can only affect particles in the universe in such a way that affects their innate acceleration. The reason for this is that if F affected the particle's speed, then we would break the symmetry that moving at a constant speed particles left on their own just move at a constant speed. Because then we could add a constant speed to something and change what F is supposed to be, and that's bad. We can't do that. Also, for the tensor fans in the audience, this also basically implies that F is a tensor. Because generally a vector transforms in certain ways that we understand under the Galilean group, and F inherits these transformations. there isn't actually enough time to go into that because we have other things to do with, just as a side note. Also, we have Newton's third law, which is like each action has an equal and opposite reaction. This basically implies conservation of momentum. That is not really clear. That is not really important for us at the moment. So we're just gonna like move on. Okay, so now we need to get to what relativity actually is. And that is essentially the following statement. The speed of light is the same in all inertial reference frames. So a bit of a history of how we figured this out, right? The thing is that in the 18th century, people figured out how the electromagnetic field works, and it's called Maxwell's equations. And the interesting thing is that, one, when you don't have any charges around, the electromagnetic field seems to just be a wave. And two, in that equation, we have the wave speed, called the speed of light. Now, in general, when you talk about waves, did I say what symmetries preserve N2? Yeah, so all of the symmetries that we talked about in N1 also preserve N2. So the important new, because think about it. Oh, right. Also, clearly, A is the second derivative of the location. So the thing is like technically, rotating your location will also rotate your acceleration direction. So it's not as clear cut, but we know how to translate A. And as long as you say that F rotates in the same way, then functionally, like if you take 2 points and calculate the distance and you move both points somewhere else, the distance is still the same. So it's like a similar sort of thing. Like physics doesn't change. Your representation under the hood does, maybe. Okay, yeah. So the speed of light appears in Maxwell's equations, and it appears in such a way that when light looks like it travels in waves. And generally, when we understand waves, waves travel in a medium of some sort. Like sound waves travel in air, water waves travel in water. And the important thing about things traveling in a medium is that a medium has like a rest frame where the sea isn't moving, and if the sea is moving like 10 kph to the right, then you have to work overtime just to keep up, right? If you want to go in the opposite direction. So for the longest time, people thought that light also traveled in a similar medium that permeates all of space. They called it the aether. But experimentally, this just did not seem to be the case. There is a famous experiment called the Michelson-Morley experiment that basically figured this out. That weirdly, even though light looks like a wave and it has a speed, it seems like that this speed is not it seems that no matter in what directions do you measure this, the speed is always the same, which doesn't really make sense if you have a medium, because a medium has a preferred reference frame, which is the rest reference frame of the medium. So there is a bit of a dark period where people wait. Hold on, I'm seeing a million people typing. Is there a question?
I can ask verbally, I guess, if there's lots of text.
Yeah.
So I'm guessing you're not meaning traveling through a medium like air or water or glass or something, because that makes me confused about things like diffraction and stuff like that.
Oh, no, don't think about diffraction. Think about how when you travel through the air and you yell, sound travels through it?
Yep.
So bye, Broncolis. There's a recording, don't worry.
The vibrations and stuff traveling through.
Yeah. So in theory, air, if light looks like a wave, then, and we understand waves to generally travel through a medium, then maybe there's some sort of medium called the aether that is all around us, but we just can't feel it like air, and it's traveling through that. What is it traveling through? This is a question that people have. But math is just math. It doesn't need to be a medium, but it's just people's understanding of waves to that point was that they traveled in a medium, so they thought there had to be one, but there doesn't. We can just, say that we don't have a medium. And because experimentally, no matter what we did, the speed of light always seemed to be constant, even in really high precision experiments. Maybe this is just a fundamental property of the universe. Maybe light just travels at this speed, and no matter what reference frame you're in, light always just travels at that speed. Now, it's important to note that light isn't special here. In our assumption, we don't want to bake into physics light being a really special case. We're just saying that this speed that light travels in has to be preserved in all of our reference frames. No matter what inertial reference frame we are in, things that travel at this speed remain traveling at this speed. So if we make this assumption, then let's check how this fits in with our Galilean transformations that describe to us things that physics respects, basically. So the first is translation in time. That doesn't really affect anything here. Because if we do a translation in time, then something traveling at that speed will still travel at that speed. Same for translations in space. The speed of light is the speed of information. That's like a whole thing. We'll get into it a bit. I'll remark upon that later. Yeah. So similarly, the translation in space does not really change your speed because the speed only affects your rate of change. Right. Okay. Yeah. Okay. I'll get to the refraction once I'm done with this point. Then we have rotation. So rotation change your direction, but not your absolute speed. So that also doesn't affect anything. But adding a constant speed breaks this because like the way that they describe it is that like if light has a constant speed and you turn on a flashlight, then you start running. Does the light suddenly travel at speed of light plus 5 kph? No, it doesn't. It still travels at the speed of light. This means that our understanding of how we go from a resting reference frame to a moving reference frame is wrong. We don't just add the speed. We need to do something more complicated because now we want to preserve the idea that when we describe going from a person standing still looking at the world and measuring stuff to a person running at a constant speed looking at the world and measuring stuff, when we change this person's coordinates, we can't just add the running speed. We need to do something else. Okay, so side note. Flugo says light refraction is about light changing speed. No, I'm confused. The thing about light being slower in a material is that this is like an effective phenomenon. Essentially, you can think about it like as if when light is traveling through glass, it keeps like running into atoms, getting absorbed, and then getting emitted, and it's like zigzagging a bit, and doing this slows it down. That is like the speed of light that we're talking about is only in a vacuum. So if you were so again, this is like not actually what's happening, but you can sort of think about it in a way that that the speed of light is like zigzagging a bit through the material, where it's going in a straight line, but every once in a while it gets absorbed by a glass atom, waits a bit, gets emitted, and continues on its merry way, and this slows it down. But this is only like the thing that you observe. It's not like the speed that the light is actually traveling at. So yeah, okay, so. We need to replace the constant speed transformation with something else. And the thing that we replace it with is called a Lorentz transformation. And it looks like this. It's a bit complicated, but here is what, but generally, if you notice that similarly, x, instead of moving to x plus vt or minus vt, that just has to do with how you define v, if it has like a plus or a minus, you multiply it by a factor called gamma, where gamma is like that function over there. And you also move around the, you also change your time coordinate a bit. Now, gamma is like, an annoying looking function, but the important thing that you need to remember is that for speed equals 0, gamma is 1. And for the speed of light, gamma is infinity, and just like goes up like that. And it appears a lot. So yeah. So if you want to assume that your transformation is going to be linear in your coordinates, which you have to assume because you wanted to preserve straight lines, and things that preserve straight lines are like linear transformations. This is basically your only option. This is all you got. So the thing is that, again, from what I said earlier, with the fact that we don't actually want to use time, we want to use c times time, so we have all of the units. And also, since our range of acceptable stuff seems to be between speed 0 and the speed of light, we generally don't talk about the speed v. We talk about beta, which is just v over c, which doesn't have any units. And then we get like this nice symmetrical looking thing about how our time and space interact with each other. Now, there's another thing that you can notice, and that is that, wait, before that, we can also just, instead of writing two equations, we generally want to write it down like this, because again, x and t are like 1 point in space-time, and it transforms like 1 point. They're like 1 unit together. And we can factor out those things to a matrix, and we can just write it down as like a matrix transformation. And also it's like just way easier to reason about when it's written like this. And it also makes it very obvious that it is actually like, a group, and because matrices are groups and they have inverses and all that stuff, so it's cool. Yeah, okay, so important thing to remember, beta is between -1 and 1.
Sorry,
wait,
go back to the gamma definition there.
Yeah. What about it?
The Lorentz factor has beta, and it multiplies beta on that matrix.
Yeah.
Okay. No, just
Wait, no. What?
making sure I understand.
What is the question? Yeah, like gamma is a function of beta. It just appears so much when you give it its own name.
Yeah.
Yeah.
Okay.
So because beta is generally between 1 and -1, because you can also go in speed of light backwards, but we can parameterize it by a hyperbolic tangent function, which, if you don't know, is like a tangent function, but it has an imaginary input, and there's like a minus sign somewhere. And if you write down like this, we can write down our Lorentz transformation with hyperbolic sine and cosine functions. We don't know why the hyperbolic sine function is in italics, but that is a mystery for another day. And for those of us who maybe have like a little bit of a physics background, because I don't think they do this all that much in math, this looks basically exactly like a rotation matrix. True, very true, Flutter. Like, if you would notice, other than like having it be hyperbolic or not hyperbolic, and a minus sign, and the fact that there is a minus sign, this is basically the hyperbolic analog of a rotation matrix. So in a very cool fashion, what we get is that the thing that we have that preserves wait, hold on. The thing that we have that the transformation that we have that gives us our relativistic analog of moving at a constant speed is essentially rotating between our space and time dimensions. Because time is a bit different, we have to do this with like a hyperbolic matrix, but that's it. It's very similar. It's really cool. And because of that, we can think for a bit and say, okay, when we rotate between in like 3D space, we preserve the distance between 2 points. Here we characterize it as the distance squared. You know, where delta x is like the distance between these 2 points in the x dimension, and so on, right? So similarly, we can ask that when we do Lorentz transformations, what do we preserve there? What do we have an analog of distance that we preserve with our hyperbolic rotation? And the answer is yes. We preserve something that we call the interval, and we preserve it between 2 points in space-time. Notice that due to the fact that the time dimension is that the time rotation is hyperbolic, there is a minus sign between the time distance and the space distance. I think that I mentioned this on the Discord before. Generally, when we talk about like the minus sign in relativity, this is the origin of that minus sign. It has some like implications later on when you want to get like a good math language of how to talk about relativity, but we're not going to get into that here because that's like a whole other thing that I don't think is going to give people a whole lot. So we can ask the question. Oh, and of course, like we can generate. Oh yeah, okay. So again, going back to I'll get to that in a second. So going back to one dimension, because we don't really need y and x, so they're y and z, they're just for the analogy with rotation. We can understand that we have 3 types of separated space-time points. We have points where the interval is larger than 0, which we call time-like separated. The canonical example of this is just a point that is just an event, and then another event happening at the same point but at a later time. We can also have points that have a light-like separation. These are 2 points, and in order to get from point A to point B, you have to travel at the speed of light. And you can also have points that have a space-like separation. And like the canonical example is 2 points happening at this 2 events happening at the same time, but in different points. But notice that this isn't only that. Like 2 points that happen one after the other, but in a really short amount of time, but are really far away, are still separated in space-like fashion. Similarly with the time-like points, that they can happen at a slightly different point, but the main question that you need to ask yourself is, if I want to get from point A to point B in like a straight line, do I need to be faster than the speed of light in order to do it? And this is the reason why we always have everything in squares, because generally it's easier to say that to talk about space-like space-like separated points as like a negative number rather than an imaginary number. Just generally easier to work with. But the important thing from here is that space-time points are causally separated. Because in order to reach one, because by definition, in order to get from one to the other, you need to travel faster than the speed of light. And in the next section, I will hopefully give you a convincing answer for why this is not a thing that can actually probably happen. If you want to, like, the classic like visual representation for what all this looks like is called light cone. This is light cone. Generally, you have your observer at the center of the coordinate system. You have the future light cone and the past light cone, and generally the past light cones are all the things that can reasonably affect you, because they can get you because they can get you in a speed slower than the speed of light. Oh yeah, there's a different monad in the Discord. It's not me, but yeah. It's called the hypersurface of the present because generally there are too many dimensions in space-time to like put on a graph. So in theory, this isn't like a plane. This is like a three-dimensional thing, but don't worry about that, it's fine. So the future light cone is stuff that you can affect. And the stuff in the hypersurface of the present or whatever, basically everything outside of the light cone is stuff that you can't affect and they can't affect you, because you are happening in a sense at the same time. And hopefully in the next section, I will give you a bit of an understanding for why that is. Also, I would like to remind you that we talked about a universal speed limit, not a universal constant speed. So why this is speed limit? The main reason is that Lorentz transformations are how we get to a moving reference frame. Similarly to how in the Newtonian version, you just add a constant speed and oh, you're running. Now, this is how, now if we want to understand what does it look like for a moving observer, we need to transform the time coordinate as well. And we're going to make the assumption that physical objects have a rest frame. If you are a physical object, you can stand still. Generally, you are always standing still. The world is always moving around you. When you are looking at the world, you are not moving and you're experiencing time pass by. So this seems to be a thing that is true for all objects in the world. So we assume that objects have this frame. And the thing is, from this frame, they can only get faster. And generally, if we look at the continuous transformation that you can do from standing still to moving at some speed, then you can go from 0 all the way up to the speed of light. But when you do that, you get to gamma equals infinity, and then you can't have a continuous transformation to there. You could think about it by like slowly ramping up your speed, and if you ramp up your speed in a continuous fashion, and you get to the speed of light, then you reach then if you try to go beyond that, you get basically a non-continuous change in your reference frame. And also it takes like infinite energy to get there, but that's outside of the scope of this talk. So the idea is that because there we have gamma equals infinity, like our idea of like making small changes into the world and seeing what happens breaks down, and it doesn't really make sense to go beyond that. But you can approach it from the other side. You can say, okay, what if I have speed of light that is 2 times the speed of light? What happens then? And the answer is that is basically what a tachyon is. The way that this works is that your inverse speed is, smaller than 0, larger than 0, and smaller than 1. And you don't have a reference. You don't have like a rest frame when you're standing still, but you do have a frame of reference when you are existing only in like one point in time, but at all points in space. Basically, like your internal perspective, if you can be said to have such a thing, space and time switch around, which is cool, but also yeah. Oh yeah. Well, also tachyons don't really exist, by the way. They're just like a theoretical thing, but they aren't. But like as far as we can tell, they aren't real. So yeah. So hopefully to the last thing, which is there is no such thing as universal time. Generally, when we learn about relativity, we talk about these things called relativistic paradoxes. Basically, because we do like a fundamental change in our understanding for how we experience the world. Suddenly, when we try to like say, okay, but what if we do some experiments, they break our intuition and make us think that something is broken. And the answer to this is almost always the fact that we have forgotten that time isn't universal and that each point has its own separate time, and that sort of thing. Because of that, I'm not going to go into detail about any specific paradoxes, but I hopefully will give you an understanding for why this is true. And then if you want, maybe you can answer paradoxes on your own time, or ask me later and I can explain it. Okay, so let us consider our first example. We have 2 events happening at the same time. We have an event at t1 and x1 that is happening at time 0 and location 0. And we have the same event happening at the same location, 0, but at a later time, alpha. So what happens if we do a Lorentz transformation? Meaning that we change our observer, who's looking at the world and understanding what is happening, from standing still to moving at some speed beta. Well, due to the nature of linear algebra, the point that is at 0, 0 stays at 0, 0. But the point that is at alpha 0, different alpha 0, suddenly happens at a slightly different place and a slightly different time, which makes sense, you know. It makes sense that it would happen at a different place because now you're suddenly running, but the fact that it's also happening at a different time is new. And this is and this is one of the new things happening in relativity.
So hang on. The idea there is that go back one slide.
Yeah.
So the idea here is that beta is like a measure of the velocities between the speeds between the two points in space-time.
Yes.
And so if I think of it like between those 2 points, they're traveling at say 10% of the speed of light. So that's how I think about those points in conjunction, in a sense.
No, wait. What do you mean between those 2 points?
Because let me see if I can phrase this correctly. The point of at 0, 0 and the point at alpha 0 are just separated by time, in a sense.
Yes. Mm-hmm.
But if 0, 0 is me, and I am moving with respect to that alpha 0 point, only I don't know, through time, then it would stay that way. But if I'm moving through space while at the same time, then this is when the Lorentz factor comes in.
Yes, it is important to remember that 0, 0 and alpha 0 are not you. These are things happening in the universe that you're observing. In the first, before the transformation, you are standing still with relation to alpha to 0, 0. And you're just like, and we're not thinking too hard about how this happens experimentally. You just, you look at this stuff, you figure out what is happening, and you say, okay, this event happened at location 0, time 0, and this event happened at location 0 and time alpha. Then you repeat the experiment, but now instead of standing still, you are moving at a constant speed. If you want, you can tell that you are moving at a constant speed because another observer who stayed in the resting reference frame looks at your location over time, and they say, "Aha, you are moving at the constant speed of beta," and that is how we know that your speed is actually beta.
Right. Okay.
And then you do the experiment again, and you wait for event 1 and event 2, and you log in your experiment book when and where both of these events happened. Is that clear?
So, but wouldn't it, from your perspective, it seem like the other observer and whatever was at position alpha 0, wouldn't it seem like that has started moving and you're still stationary?
Yeah, it did. But the thing is that because each one of these events is only happening at a specific time, it doesn't matter. Because it's happening at both time equals 0 and location equals 0, then the movement doesn't affect it in a sense. Like think about your move, like in the Newtonian analog, if you are moving, but you only check where the location is at the moment you start moving, nothing has moved yet. It's still at the same place. But things happening later will have moved because you will have moved. No? You can say no.
I think I'm a bit confused, but I'm not sure what I'm confused about.
Okay.
So I don't know how to.
Okay. Think that you are in a car, right? And you start driving.
Yep.
So the more you drive, the farther away your house is because you have driven. You'll change your coordinates. It's now farther away. But at the moment you start driving, your house is at the exact same place as if you didn't start driving because you didn't start driving yet.
Yes.
Yes. So similarly, points happening at 0, 0 because it's at time equals 0, so you didn't have enough time to get any distance from them. They don't change. But points that happen later do change because you have had time to move farther away.
Okay, but wouldn't that change if my velocity is if I'm moving away or towards whatever
Yeah,
is happening,
And the
alpha
difference
0
there
right
is that
now.
beta can be positive or negative.
Ah, right. Okay.
Yeah. Okay. So now I'm going to do something that hopefully will work. Nope. Okay. Never mind. I don't know. So I had like an error, but I'm editing it to like a different computer, and I was hoping Dropbox would like sync or something, but it didn't happen. So sorry, this slide is like a bit mangled. But the important thing to remember here is that in the moving reference frame, time passes slower. Originally, T2, the time it took you between event T1 and T2, was alpha. But in the moving reference frame, it was gamma times alpha. And gamma is a number that is larger than 1. This means that in your moving reference frame, time passes slower. This is why, for example, there's like this astronaut that was on the International Space Station for like a year and a half. And when he came back down to Earth, he was like a second younger than he would have been if he would have stayed on the Earth the whole time. There's also like a gravity thing going on there, but don't worry about that. So this is important. This is like our first example of how like time is no longer a universal thing. Different people moving at different speed will not have the same time on their clock when they meet up again afterwards.
Is it based on the velocity or the acceleration?
No, the velocity. Generally, when we talk about like simple relativity, we kind of tend to forget that acceleration is the thing. We can take it into account, but it makes the math a bit more complicated. But the acceleration also does stuff. It's just different. But it's generally a function of your, like, generally the approach is that when you have an acceleration, you assume that you assume that you have like a very like you connect like a bunch of small movements at a constant velocity, and you take the small movements to be like infinitesimally small, so you get like a derivative and an integral, and you integrate and you do it like that. If that makes sense to you. If not, like, don't worry about it. It's more complicated math that I can do in a presentation, and I feel like I'm already pushing the limit of how complicated math I can stuff into a presentation and still have it be understandable, because it's hard to understand this stuff live. I know, but I want to give like a bit of an understanding for why this is happening. Yeah. Okay. So any further questions before we move on? Nope. Okay, good. All right. So our second example, just like imagine this is on its own slide and that you didn't forget to put the space between the two stars and the word two. We have two events happening at the same time, but at different places. One at location alpha and one at location minus alpha, right? So we have like our origin point, and we have one happening a little bit to the right, one happening a little bit to the left, and they're both happening at the same time. So, oh shit. Yeah. So again, we do a Lorentz transformation, and if you really want to, you can. If you really do this, you can like follow along with the math and get this, but just trust me, if you like add all the numbers, it works out. And these are how these points end up after the Lorentz transformation. And if we just get rid of the matrices there to have it clear, we can see that we have that one of these points is happening earlier, and the other point is happening later. This is not an intuitive phenomenon, because when you like run, thing that happened at the same time still seems to happen at the same time. But because of the fact that when you do a Lorentz transformation, your time coordinate also gets mixed up a bit. Now suddenly these events have an order. One has happened before and one has happened later. But like I said before, because of the fact that if we just move in the opposite direction, beta goes to minus beta. If we change the direction in which we move, then the minus signs switch around. Suddenly, instead of T1 happening at a slight time before 0 and T2 happening at a slight time after 0, now T2 has happened first and T1 has happened second. What this functionally means is that these two events do not have a canonical order. As we said earlier, the two different reference frames, two different inertial reference frames have the exact same physical description of the universe. The laws of physics are the same. And because of the fact that depending on the reference frame, the order of these two things can change, this means that their order cannot have any inherent meaning in physics. This is why when we say that two things are separated in a space-like fashion that takes faster than the speed of light to get to them, they are causally disconnected. Because by definition, we can have two different ways of looking at the world that, in our framework at least, are guaranteed to follow the same laws of physics. They do not have a defined order, which means that they can never ever affect each other. Because if they affect each other, one has to happen first. This is the second way in which time is very much a local thing. There is no universal clock. So there's nothing keeping track of what happened before and what happened later. There's only you at a certain point, at a certain speed, looking at the world, keeping your own notes and your own clock. And if you talk to someone else, they might have a different perspective. But the ways in which your perspective differ cannot really meaningfully affect the world. They can only affect the way that you observe the world. If you want a bit of an intuition for what this looks like in practice, there's this GIF. The line moving upwards. Yeah, I know. The line moving upwards is what you think of as time's arrow. It's you, the observer, at point B in the middle, for example. This is time moving forward for you. And A and C are the events happening to your right and to your left. Now, the thing that happens when the graph gets stretched like that is the hyperbolic version of a rotation. Instead of the time direction, the x direction, like both like rotating and keeping the same angle, they do this smushing thing. And when they do the smushing thing, then suddenly A and C, when you look at their relation to the now smushed like x direction, they happen in a different order. And this is like a visualization of what that looks like, if that helps. Okay, so let's recap a bit. What were the goals of this talk?
Hang on, just a bit.
Yeah.
Is this connected to the co-moving coordinates concept that I see on Wikipedia whenever I try to understand the size of the universe?
Yeah, I'm not like super strong with the exact terminology of this stuff, so I forget what it means, but I think that co-moving coordinates, generally, if you have an object moving in space-time, I think that what co-moving coordinates are is a coordinate system that is traveling at like the same speed as that object. It also might be something else. I don't really remember. After the talk, I can look it up and get back to you, but like I don't remember now. So it's a problem that like I understand like the mathematical concept, but sometimes I forget the names because they aren't that important. But sometimes it comes up. So yeah, and also like generally after like the summation, like there's time for more questions if there are. But generally, to reiterate.
Right. Thanks.
Yeah, generally, the goals of this talk were as follows. One, hopefully you understand a bit better why symmetry is important and how we can use it to apply physics. Because generally, if we have a new theory for the world like a new type of forces we can have, our forces could not break the symmetries of our physics. If we're doing Newtonian physics, they cannot break Galilean transformations. If we're doing relativistic physics, they cannot break movement, rotations, and the Lorentz transformation. Together, all of these are called the Poincare group, but that's neither here nor there. If we do have something that breaks these symmetries, you basically have to change a very fundamental thing about the way that we understand physics, and we need a really good reason to do it. Generally, this doesn't happen often, so generally it's a really good way to constrain the types of physical forces that we can have and expect. Second is that the main conceit of relativity is that we have a universal speed limit, not on light, but on information. The reason why it's on information is because, like we saw earlier, two events that are separated by so little time, you have to break this speed limit to get there, cannot meaningfully affect each other in physics. And because of that, neither of them can know about the other at least the time where they happen. Later, they can look into the past and maybe figure stuff out. But at those two moments, they cannot know anything about each other, which is why information has a universal speed limit. And the third, we hopefully got to see some examples of how the concept of universal time, which is a base assumption in Newtonian physics, that t is just some sort of parameter ticking in the background that all functions share, is no longer a good thing to work with. Now suddenly we have to look at space at all of our points in space-time, that each relevant point in physics has both a time and space, and we have to find a new language to talk about this sort of thing and to predict events, which is a lot of what you do in relativity when you get into how you find a good math language to talk about this and work around with it. Also, generally, when people say stuff like time is relative and they're like meaning it in a relativistic sense, this sort of thing is sort of what they mean. That your perception of time is relative in the sense that it is limited to your inertial reference frame. Another person has a different experience of time, and in a physical sense, no one is correct. They both are correct, and you need to take that into account when you do experiments. Or sometimes people say that just because it's fun to say and doesn't really mean anything.
I have
Yeah. So thank you for listening.
like kind of
Any questions?
Yeah. So this could be. Well, am I like hearing myself? That's weird. It could be based on like a misconception of like some urban legend or something. But I thought that like famously Einstein was like not keen on quantum mechanics because of the incompatibilities with determinism. What are the implications for determinism if there's no set order of events? Like how can
Right. So yeah. So it is very okay. So let us go back into that is a good question. Let's go into the light cone. Yeah, okay. So when we talk about events not having set orders, this is not true for every two events. This is only true for events that are outside of the light cone. That these events do not have a defined order. But when you are inside the light cone, like in our first example, where you have 2 points happening at the same place but at a later time, or at any way where notice that in this graph time is going up and space is like the horizontal layer. That's important. Those events do have a defined order, no matter what inertial reference frame you're moving to. One of them will always happen after the other. So those two events are very much causally connected, and they do have like a deterministic order. Also, quantum mechanics is like a whole other thing, but the non-deterministic nature of quantum mechanics does not is a different type of thing than what we say about 2 points not having an order. Because no matter, even if they don't have an order, both of them have like one thing that happened in them, right? And in quantum mechanics, generally, the way that we like talk about it is that until you make a measurement, there isn't only like one thing that happened. There's like a probabilistic cloud of events that could have happened with like certain with like half of it, like 50% chance this happened, 20% chance that happened, yada yada. And then when you do an experiment, then the probability collapses and you have an event of like one thing that actually happened. But because this probability is not like rolling a dice, it's like really like the probability is like baked into the way that nature functions, probably. That means that the universe is really not deterministic, because if you do the exact same experiment twice, you could get a different outcome. If you do the same experiment a million times, you will get the same probability distribution. So it's a different type of determinism thing.
Okay. What if you look at this like light cone diagram from the perspective of like the beginning of time, like t equals 0, or like the singularity, whatever. Like wouldn't that have a set order, like from whatever would have happened from t0 to t1? Like that is because t0 is going to be at that point
So
in the
the
cone,
thing about
right?
beginning of time is that in order to like understand that well, you need to talk about general relativity. Generally, when we talk about like time having a beginning, it's important to remember that it's not like literally everything in the universe was at the same point. It was more like at this point everything was really just together, and our understanding of physics breaks down. And okay, wait, actually, sorry, I think I have a better explanation for this. You might have heard of this concept called the observable universe. The observable universe, yes, the observable universe is not the whole universe, maybe. It is the universe that is close enough to us for us to have been basically at the same point or near enough at the Big Bang. Because of this, points that were really close then can have some sort of causative relation now, because in the past we were close enough to affect each other. But this doesn't mean that all of the universe was just in one point. It could just mean that the universe was really, really dense. So it could be just like a whole grid of observable universes, and if we go far enough to the right, we can get to a place in the universe that even when the Big Bang happened, was far away enough from us to not have any causal relation, and because of that, we can't see them, they can't see us, and we can't measure that each other exists. This has like a bit of a complication with the idea, because when you talk about general relativity, space itself expands and stuff like that. But that is sort of beyond the scope of this talk. It's just I don't know if I have a good short explanation for that. But in the general idea remains the same.
Okay, so I guess it's possible that there are things that at like whatever we consider to be the beginning of time, there's like different future light cones. There wouldn't just be a single future light cone. Like you could consider different points as the point of the cone.
Yeah, generally, like you have your own special observable universe, and someone that is a slightly different location has a slightly different observable universe, because they can see a bit more off into that direction. But yeah, like the idea that like at the beginning of time was like all of the universe was like at one point is like a bit of a misnomer. It's not even necessarily the beginning. It's just that at that point we have no idea what's happening. So we'd say that is like when things start and go from there.
Yeah, you just can't backtrack any further beyond that point.
Yeah, because our modern understanding of physics just breaks down. If we have like a better understanding, then maybe we can have like a theory, but we also would have to figure out like a way to measure it, and that's really hard.
Fair.
Yeah. Right. Anything else? Yeah.
Does the effect of gravity have a similar Lorentz factor to it? I mean, are the two things
it does.
independent?
This is called general relativity. It is really, really cool. It is probably what I'm going to do at my next talk. But yeah.
Right, but what I was wondering is on that slide, can you go back to that 0, 0, alpha 0 slide?
Sure, hold on.
Just as an example.
Yeah,
that one.
Yeah.
Not this one. The one with the gamma factor afterwards. Yeah, that one. So I remember a description of the GPS satellites, right? That it had to compensate for the gravity being different because it's farther from the center of the Earth, and also the velocity.
Yes.
So I was wondering if those two effects, like I imagine they have their own gamma factors.
No, they have. Okay. So basically, they have their own gamma in the sense that your speed and the gravitational field are not the same thing, but they both happen for a very similar reason. Fun. Okay, so this is like sort of maybe like
the idea is that if they are, just to finish the question, they are somehow independent, and therefore I could compensate the contraction of one by increasing the other or something like that, and zero out the contribution, so that it looks like as if I was I don't know, standing still.
Yeah, okay. So the answer to that is no. Mainly because if you notice, the way that time slows down, it's gamma alpha. It's not beta gamma alpha, meaning that no matter if your speed is positive or negative, time still slows down in the same way. There's a similar effect for gravity, that being at a stronger gravitational field, if I remember correctly, I'm like 99% sure this is true, makes time pass slower for you. You can only really make time go slower, not faster. And because of that, if you are already in a gravitational field and you go out of it, then you can maybe do some sort of effect like that. But in general, like, because when it comes to time, you can only make it go slower, then you can't really do that. The reason for why this happens in gravity is also like a very space-timey explanation of like the things happening with your coordinates. The short version is that gravity is not like a real like force. It happens when you choose like the wrong coordinate system. So like when you are like in the car and you're in an accelerating coordinate system, you can feel yourself getting pushed back. Similarly, gravity is just being an accelerated coordinate system. But if that is not like a super clear statement, then it's just that it will be in my next talk. It's just a lot to go over. But generally, the idea is that when you are standing still, you have the shortest amount of time passing. Like when you have two events happening at the same place, one after the other, in that reference frame, that is always going to be the shortest amount of time passing between them. And any other reference frame you can go into is only going to make that time longer. And there is a similar, you can see this in this equation where it gets multiplied by gamma. And there is a similar effect when you are in a gravitational field. So just to get back into like your specific question, the only way you can organize that is if you have one point that is in a gravitational field but standing still, and you have another point that is on a gravitational field. Then if it stands still, it will have like a faster time. But if it starts moving, then you can equalize the times. But yeah, is that clear?
Yeah, I think it matches what I was thinking would happen. But I'll wait for your next talk, and be sure to answer that question properly on the next one.
Yeah, general relativity is like really, really cool. Oh, and also just I forgot to say this, but satellites are actually one of the smallest. Satellites are one of the few examples that we have of like real life, not astrophysics usages of general relativity, which is basically like what you said, that like because they are way up there in like a slightly different gravitational field. Because, FYI, when we say that like there is no gravity in space, that isn't true. Like up in orbit, gravity is about 90% as strong. Everything is just in free fall. I will get back to that in the next talk. But because they are both traveling fast and at a slightly different gravitational field, and the way the GPS works requires really, really, really exact timekeeping, then you have to take these things into account. Otherwise, your clocks are out of sync and you don't know where anything is. Because the way the GPS measures your location is basically you send the signal to 3 different GPS clocks, and they tell you how long it took it to get there, and from
Other way
how
around.
long it took
Other
it
way
to get
around.
to.
There's a bunch of satellites orbiting, and they're all reporting like where they
you.
are in their current time, and then you can triangulate your location based on when those signals arrived.
Oh, yeah, okay, cool. So same difference. Basically you use like signal transmissions because the amount of time it takes for like to get to the same thing as your distance, and from that you can triangulate your location. But you need to have that be really, really exact, and because just I don't know, it's far away, and because of that, having like these small relativistic corrections are going to matter. Like in real life speeds, like this, like gamma, which is like, you know, how much slower time passes for you when you're running. Like if you're running like 5 kph, this is going to be like an insanely small number. I don't have like I don't remember what it is, but it's like it's completely negligible. Like for gamma to be 2, you need to be like at half or more the speed of light, something like that, right? So yeah.
I have one other question, which is possibly
Sure.
related to the paradoxes stuff.
Yep. That's it.
So do we know if so I'll ask the question and follow it with like an example, right? So do we know if the speed of light applies like outside of measurements? Like, say for example, say I have I shoot photons off like with a laser in one direction, they'll be traveling away from me at the speed of light, and then I shoot photons in the opposite directions, which will also be traveling away from me at the speed of light. If it were possible to measure the relative velocity between the photons going in opposite directions, like it seems intuitive that you would get something other than C, like it would be like 2C. But it's impossible to make that
You mean
measurement.
that like what okay, you mean like what happens if you try to move in the reference frame of the photon?
Exactly, yeah. And whenever I've asked that question of people before, they've just said photons can't be a reference frame, and that's a very unsatisfying answer to me.
Yeah, unfortunately it's also the answer, but hopefully let's try and understand why that is now that we have like a bit of math to work behind us. So okay, wait, hold on. So so we see these, right? We have 2 events happening. Wait, sorry. I think the previous one's actually a better example. Right. Okay. So here we basically have a person standing still. And you know, and at time 0 he is there, and at time alpha he like screams or something, right? This is like a thing that happens. This is an event that only makes sense because there is such a thing as a resting reference frame for this person. The thing is that the reason why photons don't have a resting reference frame is because no matter what Lorentz transformation you do, like the photons are still traveling at the speed of light. So no matter how fast you try to move your coordinates in every single reference frame, the photons are still traveling at the speed of light. Because of this, through Lorentz transformations, you cannot get to you cannot get to a reference frame where the photon is standing still. This is like a math thing. This is like why there's no such thing as a resting reference frame. But maybe that's like not intuitive because intuitively you feel like you should be able to like catch up to them. But if you like do the math, you understand that like velocity addition in relativity doesn't work. So for example, if you know that you can like press a button and make yourself go 10 kph faster. So if you press that button once, you're now at 10 kph. If you press that button twice, you're now at 20 kph. If you press that button again, you're now at 30 kph. But the thing is, if once you take into account relativistic corrections, you basically get to 10 kph plus 10 kph is not 20 kph. It's like a bit less than 20. And once you get up to relativistic speed, you basically get closer and closer almost to the speed of light while never actually reaching it. And because of our understanding, you remember our understanding earlier when we talked about the speed limit and we talked about the concept of like a rest reference frame, and how when you are at a resting reference frame, basically the way that you understand other frames is by making like a continuous transformation from standing still to other ones, because this is how like you work your understanding of being at rest with other ways of moving around the world. Due to the way that our math works and the way that our theory works, photons, by definition, do not have a resting reference frame, because if they did, then A, they would break the constant speed thing, but B, most importantly, you can't get from a resting reference frame to a frame that is traveling faster than the speed of light. So because of that, these are like two fundamentally incompatible concepts. This is like one of the really strong examples of how our concept of like time as like a thing just happening in the background just isn't true anymore in relativity. And if all of this, and if this sort of like explanation does not really give you good intuition for it, then maybe I can think and come up with a better answer. But generally what happens is that once you like work with the math enough and see like a lot of examples, you form like an intuition for what time is from a relativistic perspective. And then you stop being bothered by the fact that this isn't a thing anymore.
The button analogy that you used about like +10 +10, and you end up with something that's a little bit less than +10 actually was quite helpful for understanding that.
Cool. I'm glad to hear. Yeah, there's if you want to like look at what this exactly looks like, look up relativistic velocity addition formula, and you get like the exact formula. And if you want to like look into that a bit more, but yeah. So any more questions? Okay, guess not. Cool. So hopefully that helped you understand a bit more about what relativity is.
Water fucking tensor.
Oh yeah, sorry. That is sort of outside of the scope of this talk. But basically, remember when we talked about symmetries and how like things transforming need to respect the symmetries? Well, basically the idea is that things transforming do not have to transform to the exact same thing. Like for example, your location, when you rotate, it moves to like a different location. But things that you can measure stay the same. But because in our underlying like physics theory, we have like our easy descriptions of the world. And those descriptions can change without changing like things that we can actually measure. We describe the ways in which these things change as being tensors. Generally, because we want to talk about our transformations as like groups, we do like this thing with group theory where you say, okay, any group we can represent as basically some sort of matrix, and we can represent all of our transformations by like applying matrix operators. And that is sort of where like conceptually tensors come from. In practice, often you don't want to group concepts in just a vector because you have like a bunch of related concepts. So a vector isn't enough to describe them by like having a vector rotating. So you want to have like higher order like matrices. Like for example, a matrix is like a rank 2 tensor because it in a sense contains two different vectors at the same time. And when you apply rotations, both of them like rotate. But you can have like even more indices for like even more complicated concepts. And the general idea of this thing that has a transformation that you understand in a good way under the symmetry group of your system is what a tensor is. And in real life, you can only really measure scalars, which are things that don't transform, because those are the only things that like physics keeps invariant. So things like the distance between the points is going to be a scalar, stuff like that. That sounds like it didn't help.
Yeah, that might be a topic for a different talk.
yeah. This is why I cut the tensor part of the talk, because even though I like them, because I think it's cool math, I don't think it's something that can be well explained in like a talk format. It's something that you need to like see a lecture and then do some homework and then you get it, because then you're like, oh, okay, all of the math stuff fades into the background and I understand the thing. But like tensors in a sentence are things that have well understood transformations under the symmetry groups of our physical system. That is what a tensor is.
Use a whiteboard next time.
No. Do you know how long this would take under a whiteboard? Are you kidding me? It would be like 3 hours from now, and I would just be getting to the third point.
Okay. Annotate your slides.
So
have pre-prepared slides that you annotate live with a pen or something.
like Khan Academy style. We should move to the next talk. Thanks, Monad.
Yeah, but there isn't the next talk.
There is no next talk. This is the last one.
This is it.
Oh, I thought Marco was going to present.
No, he didn't have time to prepare it in the end. He's going to do it on the next one.
Yeah.
Yeah. This is part of the reason why I was fine taking so many questions, because I knew that I wasn't blocking anyone else.
Okay.
Yeah.
Any more questions?
Not related to the talk.
Okay. Do we want to cut the recording here, or do we want to?
I think we can cut the
Keep it
recording
going.
here. The recording is like for talks, not for everyone to be able to spy on like random stuff.
Yeah.
That's what the next Discord is for, where they can read the text.
It's already going to take like 7 hours to upload.
Yeah.
Okay, I'll turn
Okay,
mine off as
cutting
well
it.
then.